hello, everyone. So we have a full house here. We should say good afternoon or good morning in the United States. So please join us. Today we have Kevlin Henney here with us, and let me a little bit introduce him. So he's an independent consultant, speaker, writer, and trainer. Kevlin, you have co-edited 97 things that every programmer and every Java programmer should know. So
this is correct, yeah.
What are the three main things?
Oh, I can't do that, because I can't do that. One, because that's almost impossible, but two, because that shows favorites, because by a ridiculous coincidence, both of the books, 97 Things Every Programmer Should Know and 97 Things Every Java Programmer Should Know, had 73 contributors. I like to keep numbers on things, but yeah, I don't know how we ended up with exactly 73. But that means if I choose three things, then I'm going to be saying the other 70 are less important. So I'm not going to do that.
All right,
but
okay.
I will quote 3 or 4 things in the context of this talk today. And that's different because that's in the context of what I'm talking about, as opposed to, what are the 3 things that they should know? So yeah, I'm going to cheat with that. Yeah.
Okay. So I think we are ready to go.
I think we're over full. Yes.
Yes. So today we're going to hear software architecture for developers. And,
Absolutely. Yes.
Stage is yours. I hope everyone found a seat over here. And,
found a seat or made a seat. You know, I talking about developers being creative. Well done. Okay, right. Let's make it so. Somewhere there is something that transitions to this. Excellent. Good. Yeah. Nice choice of colours there, Kevlin. Go on. Yeah, so these days you're not anybody if you're not coining a phrase. And I was asked, Nerenga said to me, Kevlin, could you do a software architecture for developers? And I said, yeah, but that's a really dull title. So I'm going to make that a subtitle. And it's just like, everybody's kind of like, dev this, dev that, dev arch. Excellent, you heard it here first. So I want to target this. I do a lot of talks on architecture. And a lot of workshops on architecture. And that doesn't mean I'm telling people, here's how to do with this technology in this particular style. What I found to be most valuable is, the thing that is invariant with time, is how you think about it. Architecture is about people, and it's about reacting to a situation. This is my main motivator. If you think good architecture is expensive, try bad architecture. Now, what's interesting is that immediately causes you to think, because it also tells you where the challenge lies, because often people will do this. In fact, you can even substitute other phrases for architecture. If you think good thing that takes effort is expensive, try bad thing that takes effort. Okay? You can do that for unit testing, code quality, anything. Just pick some aspect of your development that sometimes people, that's a bit of work, or maybe we can just skip that for the next release and we'll do it later. Here it is. The point there is that we are talking about cost and time. And cost, for most developers, I think it's not very motivating. I think telling people, hey, this is this many euros, that many euros, it's too abstract. It's a bit like reading things in the newspaper about how much certain things cost or how much budget the government has for certain things. These are abstract numbers. So let's relate what cost really means from a personal perspective. Time and effort, that's what cost means. Okay, you can relate to that. It's just like a bug costs this much money is one thing. A bug costs me a week of feeling like I've made no meaningful progress and is incredibly annoying and frustrating. I know what that costs. I can relate to that. So whenever I use the term cost, I want you to think not just in terms of the financial thing, unless you happen to be talking up, but in terms of thinking about personal effort and time. The other aspect that I want to emphasize. By the way, this comes from a paper. I think we might close the door, because there's a little bit of noise. There's also, I also think I might take breaks soon. I'll talk about breaks in a minute. So, this is from a paper that was published in the late 1990s, and a lot of people don't know it's by Brian Foote and Joe Yoder, who are 2 very key members of the patterns community. And the paper is called Big Ball of Mud. Now, most people have not read the paper, but everybody's heard about the Big Ball of Mud. Oh yeah, that's our system. I've seen the Big Ball of Mud. I work on the Big Ball of Mud. Another name for legacy. But this paper is actually a little more insightful and inspiring than you might think. But this is one of the early observations. Now, I'm going to go back to one of the great logicians of the 20th century, Alfred North Whitehead, who, with Bertrand Russell, produced the ill-fated Principia Mathematica, which is not the subject of today's talk. We think in generalities, but we live in detail. This is the important connection. When we want to relate developers and development and architecture, we are trying to make a connection here. Because sometimes people, oh, architecture, that's just the big hand-wavy stuff. Okay, that's the big picture stuff. It's like, I'm going to try and convince you, if you're not already convinced, that that's not actually what architecture is about. That it is intimately about the detail. Okay, stuff about me. This is me standing up against a black background. This is so delightful because I had to show this during the whole of the pandemic, to show people this is what I look like in my office, but this is what I look like when I'm standing up. It's not much different, except my choice of t-shirts tends to vary. If you want to get in touch with me afterwards, these are the contact details. Technically, this is qualified as a workshop. I don't think we're going to do a lot of work here, but I might ask you some questions in the latter part. But what I tend to do with anything that's formatted as workshop, I will make the slides available. I will give you a URL later. I will give you the URL. I could give you the URL now, but there's about 5 slides up there because I'm going to change the slides as we go through because I'm agile. That's what I do. Those of you who were at yesterday's keynote will know that's what I do. So I definitely do respond to change over following a plan. Now, what qualifies me to talk about software architecture? I've got 2 books with my name on the front that have the word software architecture. There you go. That's good enough. There's no formal definition of what we mean by architecture. There are a number of different bodies and institutions that try to say this is what we mean by architecture, this is what we mean. The patterns thing, you've heard me mention a couple of times. Now, I'm not specifically going to be talking about patterns today, except as a thinking model. I will come back to those in connection with ADRs, architecture decision records. We've already mentioned 97 things and the other 97 things, but let's talk about definitions. Oh yeah, breaks. I said I was going to talk about breaks. My plan is that this is supposed to take 3 hours. I'm not going to keep you here for 3 hours because I believe that we are all, certainly Lithuania, I believe, is a signatory to the Geneva Convention. And I think it is cruel and unkind and unusual to keep people here, especially in an oxygen-deprived environment, which it's going to be. And originally, Nanga told me that she wanted to do this in 2 halves. I will try to do that, but if I see some of you passing out through lack of oxygen, we may restructure. But the idea was that our break will be out of sync with the main breaks. If you decide this is too much, or Kevlin is just like, sending me to sleep, or this carbon dioxide is sending me to sleep, then feel free to leave at any time. We'll just look at you as you go. We'll just be a moment of silence, but we won't judge you. We'll just look at you as you walk. No, but if you do, really feel free to opt out. But I will kind of do a break around the halfway point, unless I think, this is getting crazy. We need oxygen and caffeine, the fundamentals of life. We will do that differently. So, at the moment, I'm thinking we're doing this in 2 halves with a 20-minute break in the middle. If we need to change that, we will change that. So let's talk about this thing. Architecture is a term lots of people try to define with little agreement. So this is a quote from Martin Fowler a few years back in his Patterns of Enterprise Application Architecture. And what he's identifying there is the problem that this term does not have a single point of origin. What I mean by that is that sometimes you can actually trace back where a phrase comes from. In fact, I mentioned DevOps earlier on. We can actually trace back the people that created that term and coined that term and the context in which that was created. There are certain terms in software that we are able to go, oh yeah, here's the history. Now, that doesn't mean that the word always means the same as it used to. Words do shift in their meaning, but we can trace its history very easily. The problem with software architecture is it's a very natural metaphor. The use of architecture is a very natural metaphor. We find it across many disciplines. It's not something, as is the case with most metaphors, it's not something that somebody invents. It's something that kind of lots of different people kind of, oh, this is a good way of describing this. And we see the term architecture as used from the 1960s onwards. And different people mean slightly different things by it. Nobody gets to say, this is software architecture. So we can't really say what it is. We can say which ones we like, so we can express a preference. But the one for me, the way that I tend to look at things, is by utility. Which are the definitions that are useful and help me think about my system? And I do this for a number of terms. There's other terms like unit testing, for example. What is a unit test? Again, same challenge. That doesn't have a single point of origin, but there are some definitions that are more helpful than others. They help us, by talking about them, move forward. And so software architecture typically breaks down, as Martin describes, there's a bit more convergence, not little agreement. I think there is more convergence these days, but what he highlights is still true. One is the highest level breakdown of a system into its parts. In other words, the big picture view, the big box diagram. And then the second one, the other, decisions that are hard to change. I prefer the second. In fact, I think the second one is the useful one. I don't actually think the first one is that useful. To the point that when somebody shows me a picture and says this is the architecture, the one thing I know is that they have not shown me the architecture. They have shown me a view of the architecture. And that's a really important idea. There's a bit of philosophy in there as well, but the idea is don't mistake the view for the thing. Sometimes there is more to the thing than you can already see. And they have shown me a view. My question is, what other views are there of the same thing? This one relates a little more to what I'm interested in. Decisions that are hard to change. In fact, let's go to this definition from Grady Booch, which is the one that I tend to use most, because this one is the most useful. All architecture is design, but not all design is architecture. Right, now what does that mean? Let's try a couple of things here. The first is I'm going to try drawing on the screen. The second is I'm going to try and get to the screen that I'm going to draw on. Oh, excellent. That's a good sign. A blank screen. It's intentional, don't worry. Okay, so, no, that's completely the wrong thing. Ah, there we go. Excellent. Right. So, what I want is this idea that, okay, squiggles. Awesome. Right. What we are saying is that there is, if we like, this is design. Okay, all of the stuff is design. But there is a particular subset of design that we are going to call architecture. So, in other words, just for reference, that means that I'm using this rather than the flip chart. One, because it might be more visible for anybody watching online, but two, because when I drop out the PDF at the end, you get the diagrams as well, including my awesome personalized font. Yeah, I don't think I'm selling that one, am I? So, all architecture is design, but not all design is architecture. Okay, so if that's the first thing. Design and architecture are not separate. One is a subset of the other. But our question is, how do we separate the two, or rather, how do we define that subset? Because I drew it with a kind of like a squiggly border to suggest that it's not a hard, fixed boundary. It's not like you are now leaving the architecture sector and there's a border control or something like that. It's not that clear. It's not that concrete. But there is something that we can do. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change. Oh, that's the one. That's the one. This is what makes this so useful. That's cost. That's hard. That's how hard is this to change? How much effort does this take to change? How many developers? How much time? An architectural decision is therefore one that appears on the radar, as it were. Everything else is kind of like, it just falls into the flow of your work. Yeah, we'll fold that work into the next sprint. Architecture is like, that's the bit where, somebody says, oh, we need to change this, and everybody around the table goes, you can tell from their body. That's how you know it's architecture, because they know there is work there. They know there is effort. It's visible at a level that might require clearance from other people. It might affect other teams. It affects your schedule. There is something going on here that is big. Oh, okay. That's significant. And it's funny because sometimes people will go a long way to try and avoid those. And guess what that does? It changes the architecture. Because what happens is that And this is the important thing about the big picture thing, why I don't believe the big picture view is the valid view of architecture, because not all these things are big. It turns out that most architecture is created by doing lots of small things, lots. It turns out when you do the same thing that's small and everybody does it, that is now your architecture. Yeah, it becomes a big thing. If all the developers avoid a particular part of code and work around it, then their workaround becomes the new architecture, because that's how we all work. We have now reshaped the system, and now that's the hard bit to change. So the interesting thing is that we also, by doing these micro optimizations or avoidances, actually create our future problems as well. But we don't see that. It happens on the day-to-day. We don't see the year-to-year. But it also tells us something else. We don't know what is going to be the hard thing to change, because we don't yet know what we want to change, because this may come as a shock to some of you, we're not very good at predicting the future. And that is the challenge. That is the difficulty, and that is why we end up with the idea, sometimes people say, oh, architecture is about creating a structure that doesn't change but works for the future. Yeah, good luck with that. Okay? That just doesn't fly. That's just not even reasonable. Almost every architecture that has been created with that in mind has ultimately failed at some point, sometimes sooner than later. The idea is, well, how do we react to this in a way that's meaningful? In other words, we're going to learn the answer to our questions is in the future. So that immediately implies that there's a development process. Now, quick check. Who was at my keynote yesterday? A reasonable number. Who was at my talk this morning? Okay. For those of you that were lucky enough, and I say lucky, and I'm obviously assuming something there. No, I'm going to say lucky because you're still here. I mean, what do I have to do to get rid of you? You are going to get a very complete picture, because these actually form, you have discovered that there are 3 pieces to the puzzle. You've already got 2. At the end of this afternoon, you claim your prize by having the 3rd, okay? Actually, I'm going to reveal a little more this afternoon because it's longer, but that's the idea. These pieces all fit together. And yesterday I was talking about the idea that the future is where we find the answers to the things that we want. This is why we have development processes. Today, I reinforced that this morning. That's the thing. The architecture we want is in the future. We know about it in the future, yet we have to make decisions in the present. In the absence of a time machine, we're going to have to do something hard. We're going to have to actually iterate over what we're building. In the presence of a time machine, well, why would you do anything like software development? Go visit the dinosaurs. If you have a time machine, there's much more fun to be had. So there is a point here that we've got a basic idea of understanding change and understanding the nature of change, the scale of change. It's only when you start undertaking that you go, yeah, that's quite big. So let's have a look at some definitions. And what I've done here is I've taken definitions from when I run workshops, and I've kind of shaped them into my own words, but some of the observations I've had from people about what do you think architecture is after we've run kind of the workshop for a day or two. Software architecture determines where developers will spend their time. That's an interesting way of looking at it. Your architecture shapes. If you buy into this idea of the metaphor, no metaphor is perfect. So one must always be careful with metaphors. But of course, metaphor is not perfect, because then it's not a metaphor. If a metaphor is perfect, then it is the thing. Yeah. So there's no such thing as a perfect metaphor. But the thing is that we sometimes miss the fact that architecture, the point I made this morning, architecture defines a place where we live. We often think about it just as structure and purpose. We understand that school buildings are designed according to different criteria to hospitals. Okay? We understand that there is a different skill in that. And actually, in the real world, architects are trained differently or have different skills they draw on for these. But what we're saying here is also developers live in it. Where are you going to spend your time? That's the shape of the building will tell you where you spend your time. The shape of the code will tell you where you spend your time. So that's kind of an interesting one. A good architecture. So here's an interesting question. What do we mean by good architecture? This is, again, something I spend a lot of time with in longer workshops. A good architecture is one in which the things that are costly to change and the things that need to be changed often are not the same. Now, this is quite subtle. Let's unpack this a moment. Based on the Grady-Booch definition, there is the idea that there will always be something that is hard to change and costly to change. If you like, those are the foundational decisions. You can't have an architecture that doesn't have a thing that's hard to change. Okay? We can actually see this very, very simply by thinking of some examples. And it also highlights some blind spots that we have, things that we don't see. Very common thing when I run these workshops, I say, tell me things that are architectural, and also tell me some things that are not. Quite common, people will put up things like, oh, programming language is not architectural. Okay, sure it isn't. Right, so that 1 million lines of code that you've got in Java, let's change that to C#. Oh, well, you can't do that, it's going to cost a lot. Well, that's kind of architectural, isn't it? Oh no, that's just the language. Look, what you've just described is you've described the fabric of your universe and you're saying it's not important. A system written in C# cannot easily be transformed into a system written in Java because it is written in C#. It is fundamentally different at a particular level, and it actually shapes a number of architectural choices. If I work in JavaScript, there are a number of things that I won't do. I won't go to bed on time, I won't eat well. Sorry, that's the wrong list. If I work in JavaScript, I don't sit there going like, oh yeah, let's think about threading, because I can't. It doesn't do threading. That's just not a thing. A language is not merely a way of arranging if statements. A language any language worth knowing comes with a model of how you think. There are things I can do in JavaScript. It's a very flexible language. Some might argue it's too flexible, but it's a very flexible language. There are certain techniques I can apply there that if I were to work in C, it's just like, oh, okay. I'm going to have to basically invent a framework. Okay? I'm going to have to work around the language. And we find that sometimes things are very easily mapped. Microsoft's COM in the 1990s is basically C++ vtables. That's why it doesn't really scale to other languages or work with them. If you get a team and you say, in fact, we can actually see a tale of two telecoms. You take Ericsson, where Erlang was invented by Joe Armstrong, and you take AT&T in the States, where we have C as the dominant language. These companies are both involved in telecoms. They're both involved in high availability servers. Guess what? Their architectures are different. And some of that comes down to, oh, actually, some of the decisions are actually around the language. They are fundamental. The language is the ingredients. So, yeah, your language matters. Now, you can make it matter less. So the example I've used for a number of years, and unfortunately microservices came along to make my claim more credible, is I said, well, just imagine developing a system where I separate out tasks into multiple processes, and then I communicate with processes. And this process is written in C++, this process is written in Java, this one's written in Perl. How significant is the language choice? Oh, significance has gone down. That's great. We have no architectural constraint on language. Yeah, you've now got a new architectural constraint. It's called the protocol and the process model. What you've done is you've moved the hard bit somewhere else. Okay? There is always something that you have to lean on for everything else to kind of stand up. Okay? When I say something, I mean some things. Now, what we can do is we want to minimize the set of significant decisions that everything does rely on. Sometimes we don't know that because it's invisible to us. We don't see that. But there are other things as well. If we find that we are having the frequent changes we're making from requirements or other demands of the organization, if those are always really heavyweight and difficult, then our architecture is not well matched to the needs that we have. We've learned it's just like, well, this is always really hard. We should change the architecture. Oh, we can't change it. We've got the wrong architecture for the job. So you need the architecture that makes the things that you do easy. An architecture that does not do that is not the right architecture. Now, that doesn't necessarily, we need to be very careful with words. I've used the word good. I'm a little cautious about that, but I'm very cautious about using the word bad. Because what we might find is it's mismatched. In other words, it doesn't mean that this is a bad architecture. It just means that for our changes, if we're frequently receiving changes, and those changes are always, always hard, then our design structure has not matched our needs, our requirements over time. And guess what? We discovered that later rather than sooner. Well, this indeed happened with an organization that I visited a number of years ago. They said, hey, Kevlin, we have a technical debt problem. We're going to look at technical debt in a bit. Our deliveries are slowing down. Everything's taking more and more effort. And we spent a couple of days, and I very much discovered by looking into the code. In fact, that was the thing. The first day, it was all whiteboard talk, classic architecture. Yeah, talking the higher ups and the architect. Yeah. We went out for dinner, And I said, I'd really like to see some of the code. We've talked around it, but we haven't seen the code. And I'd also like to speak to some of the users. What, you want to speak to the users? Okay, we'll see if we can find some. They're probably locked up in a building somewhere. We'll go out and find them. Now, what was interesting is that what I discovered, pairing with another guy, yeah, we paired, we tidied up some tests, he showed me around. The rest of it's a .NET system. C# looked really good. Good use of NUnit. Tests were pretty clean. And I couldn't see any issues with the code. And then this guy, he said, oh, let me pull this method up for you, Kevlin. This is what I'm talking about. This is the kind of stuff that's causing problems. I have to put up with this stuff on a daily basis. He said, look at this method. Look at the size of it. It was 40 lines long. I know companies that would kill for code that small. He is complaining because this is a screen full. That was what I often call a moment of calibration. Oh, what you define as bad is actually not that bad. Or rather, we're on the same wavelength. Yeah, we could improve this. But actually, if this is the worst you can show me, your problems are not the problems you think you have. And that was reinforced by then speaking to one of the users who then told me the history of the system. It turns out the system had been designed for a completely different purpose. But and therefore it had been originally designed for that purpose, to make those things, those changes, those concepts, that particular entity model easy. And guess what? Over time, its scope had drifted. And now you're effectively trying to add something that doesn't fit with the ease, the grain, if you like, if you think about this in terms of wood. The grain of the system was that way, but they were having to cut across the grain. It was naturally hard work because it didn't fit with the way the system was designed. And I said, you don't yet have an unmanaged technical debt problem, but if you keep on doing this, you will. But now is the time to realign the system. Your system's abstractions are not where they need to be. Your system, your event model is not where it needs to be. And so it was a really interesting thing about discovery, but also the changing nature of that. But also there's an awareness there. I've also had the opposite case of a complete lack of awareness of one guy trying to, he wanted some advice on a state machine. Funnily enough, this was telecoms. And he said, yeah, could I trouble you, Kevlin? I was doing some technical coaching in this company. Yeah, not a problem. He said, yeah, I've got this state machine I'm porting from C into C++ for our current system. I just wanted your advice on a couple of small points about C++ and stuff. And I said, yeah, that's absolutely fine. We can look at it now. And it was going into lunch. And he said, I'll see you after lunch. Of course. I mean, I've got nothing else to do, but obviously he has a life. As somebody who's an independent, I have no life. So therefore, I have plenty of time. So I thought, right, okay, he's got things to do with lunch. That's fine. After lunch, he turns up and he's got a thick printout. So he's real old school. Everything else I'd done at that company, we used screens and such devices as computers. But no, he chose Forest. And he walked in with this side of tree. And he said, okay, so this is the function. And he did not blink, he did not laugh, there was no humor in his eyes. I'm sitting there going like, he's actually serious. And he said, right, so the bit that I wanted to ask you about, and I'm sitting there going like, that's a function. In English, we have this phrase, rearranging the deck chairs on the Titanic. The fucking ship is sinking and do you want the chairs like this or like that? We're dying, there's an iceberg, people are dying. But if the chair is like, and it was like this monster that had taken all of lunch to print. That's why he wanted it the other side of lunch. And I'm sitting there looking at this function and it's just like, that function is architectural. So here's the point. What we want is that we want an architecture that makes the things that we want to do lots, it makes the changes that we normally want to do easy. That's what we want. We want that alignment. But we don't necessarily know that in advance. Now, that doesn't mean we don't have knowledge that we can apply. It just means that even with our best knowledge, we're not going to be 100% right. But the more novel a system is, and the more likely it is that people adapt it to their usage, the less your ability to anticipate future actions is going to be. So you better go in with the opening position of, we're probably wrong. But that's not a problem, because we can be probably right given time. For developers, a good architecture is one that allows them to attend to work in the present to build the future rather than fighting the past. This is my favorite way of looking at this. Most people are programming in the past. You sit down, what are you doing? Well, I'm trying to understand something that somebody built. I'm supposed to be building a future, but actually what I'm doing is dealing with the past. So I've noticed this in various companies and increasingly made informal observations about this, that given an 8-hour day, you're probably spending at least 7 hours living in the past. There is 1 hour that you're contributing to the future, and that's on a good day. Okay? So that becomes our friction. That becomes the thing that is holding us back. So I want an architecture that allows me to not have to grapple with the past, not to re-understand something somebody else has already understood. Okay? So this is a knowledge-based thing. Somebody else has built this. What do I understand about it? The better the code, the better the structure, the clearer the intent, the more able I am to work with it. The harder it is, the more moving parts and complexity and subtlety, the harder it is for me to get it right, but also the harder it is for me to know it. We often define legacy systems as ones in which we lack the knowledge. The people who knew what was going on have left the building. Okay? So there's a loss of knowledge associated with them. Software architecture is the set of decisions that will shape the cross-functional, sometimes people use the term cross-functional, I'm going to come back to that one later, properties of a software system. Any dependency in an architecture can be both a benefit and a liability. This is a really important point. This depends on this. It doesn't matter if it's this function calls this function. It doesn't matter if we're talking this library imports this library, this process calls that process. All of these are dependencies. If you don't have dependencies, you don't have a system. You have a set of parts. So there has to be some coupling. But the point is, not all coupling is necessarily good. And too much of it gives us a dependency management problem that manifests in builds, in deployment, and how bugs propagate. It makes things hard. If in order to make this change here, I have to know about that, and that, that's going to be far harder than I make this change here. I only have to know about that. In other words, how much, again, this is a knowledge thing. It's quite literally, when I am sitting here trying to make a change, how much do I as a developer need to know? Now, there's a curious consequence to this that a colleague of mine, Alan O'Callaghan, I used to do architecture and patterns workshops with him, kind of pointed out, and I hadn't really thought about it, is that sometimes we will quantify a system in terms of the size, number of classes, number of lines. And that gives us one view of the size. But what Alan kind of helped me understand is that depending on the dependencies, a system can accidentally seem larger than it actually is. Okay? In other words, I can take a 100,000 line system and make it feel like a 1,000,000 line system. That's not a good thing, by the way. Yeah? What you want is the other way around. You want a 1,000,000 line system to feel like a 100,000 line system. You want it to feel smaller. You go, oh, here's everything I need to know. It's all in my immediate locale. And there's an interface there. I don't know what's on the other side of that interface, and that's fine. Whereas, oh, and there's a thing I have to know, and there's a thing that it depends on that I have to know, and there's another thing that somewhere somebody's injecting all kinds of stuff, and and there's another thing. Wow, changing this is really hard. The level of knowledge and intricacy that I have to get involved in is very high. It feels big, even if it's actually surprisingly small. So there is this very simple idea about a perceived size. Literally, how much do I need to know in order to work in this space? And the more that I need to know, the bigger the system feels. You want your systems to feel small, even if they are actually technically large. Okay, team skills determine the effectiveness and appropriateness of an architecture for that team. Oh, this is a good one. Because sometimes we have the idea that an architecture can be independent of people. This is a good architecture. And we end up with this kind of ivory tower architecture. And this was an interesting one. I've had this one a couple of times where you end up making a decision. It's just like, actually, what are the team skills? And in fact, I used that example, Erlang. I mentioned the Erlang program. Has anybody worked or just even played around with Erlang? Okay, there we go. So if I said Erlang is the best language for this thing because it supports fault-tolerant architecture and all the rest of it, what is our biggest problem? We have no skills. Oh, yeah, sure we can change that. It's just like, yeah, you know what, that's not going to work out. Because that becomes our bottleneck. That becomes an issue. The company that I mentioned, the guy with the C function that was so big, they had an interesting problem. Their original architecture was supposed to be predominantly Java. It's supposed to be JVM based. And they're supposed to just have C++ for the little systems bits that they needed. But they needed a custom JVM. That JVM was not stable, which is a problem. If your whole product relies, remember I said dependencies can be, oh, we rely on this JVM, that's not our problem. Oh, guess what, that JVM is not stable. Suddenly it's become a huge problem. In other words, if that doesn't stabilize, you don't have a product, given your current architecture. It took them a while to figure this one out, and eventually they decided to go, oh, we're just going to do C++ all the way through. That's not unusual for a telecoms architecture in that period of time, it was the 2000s. There's only one problem. They've just recruited a whole load of Java developers. Yeah. The number of C++ developers is in proportion to the original intended architecture. They have about 20%. It was going to be basically 80% Java, 20% C++, and that's the ratio they have of C++ developers to Java developers to C++ developers. Now we're doing 100% C++. And I started working with some of these people. Oh, and then they suddenly realized it's going to take too long. Let's get some more people in. What skills did these people have? Oh, we've never heard of object orientation. We've been doing maintenance in language that I'd never heard of for the last 30 years. Okay. And I remember saying to one of the guys involved in the project, I said, I think that in about 12 months, the developers will be ready to start developing the system. He said, that we can't do that. We've got to deliver in 12 months. Good luck with that. Yeah, that company did not survive. Because the point is that it was the wrong architecture for the team. It was the wrong technical decisions. These guys had not worked on distributed systems. They had not worked on the messaging architectures that they were using. It's not that people can't learn. It's just that if your original schedule was dependent on everybody, we're all hitting the ground running and we are going to have exactly the architecture that we intended, the problem is that didn't fit. So what makes an architecture suitable or less suitable for a team? It's a fit. You can't just say, this is a good architecture, show me the team. Oh, that's a great architecture. That's going to fit the team really well. There's enough learning in there, there's enough progress, but also there's enough familiarity, there's solid ground they can build on. Unless your whole goal is we're going to break new ground, we're going to do something different. But then you account for that in your structure and your team choice. But if you suddenly say, hey, we're going to build this, and these are the people we've got, and it doesn't fit at all, it's just like, that's not going to work. That's not a good architecture because it doesn't fit the team. It doesn't fit the organization. A good architecture is one in which the decisions that define the architecture support developers rather than one in which developers work around the decisions. In other words, creating their own decisions. And that's the point. We are all creating the architecture all of the time. So let's have a look at another definition, another set of definitions that give us insight into architecture and its structure. Architecting enterprise solutions, patterns for high-capability internet-based systems. Now, I'm not necessarily recommending this book, not because there's a problem with it, but because it's from 2007, and it turns out that a lot has changed in 15 years about the nature of how we build internet-based systems. Okay, so you won't find much cloud here, you won't find any microservice. Yeah, there's a whole load of stuff. But the thinking, and particularly the early sections, and one of the things I really like is the definition that they use. So Paul and Andy use this definition. Our position is that an architectural definition is something that answers three questions. I like this way of approaching it. Rather than saying, this is our architectural definition, what we're going to do is, okay, three questions. Whatever your answer is, that's your architecture. Okay? That's a really interesting way of looking at it. You've made it a process of inquiry and discovery. Okay, number one, what are the structural elements of the system? What are the things? What are the components? What are the ingredients? If you were to draw out things on a diagram, what are the boxes and the bubbles? That's the things. And that can mean anything. We could be talking services, we can be talking processes, we can be talking classes, we can be talking functions, we can be talking layers. In other words, the nouns that we would normally name at any level, what are the ingredients? How do we combine them? How are they related to each other? Components plus connections. This is one of the kind of classic views of architecture. Connections, what are the lines we draw between them? What do those mean? And that, again, is every level of scale. Oh yeah, this is HTTP. That line is HTTP. That we're going to talk about that, and we pass this XML over it. But to that one, we pass this JSON. That's what we do with this. This is asynchronous. It is also this function calls that function. That's a relationship. That is a connection. This class inherits from that class. That is a connection. This implements that interface. That is a connection. This runs in a separate thread to this, and they communicate via a queue. That is a relationship, that is a connection. So quite literally, if you think about any diagramming or sketching notation, formal or informal, that you use, it's normally things and lines between them. We're basically asking, what are the things and what are the lines between them? What are the semantics of these? But that's 3 questions. We've got 2. For a lot of people, like, yep, we've done architecture. It's components and connectors. What, how, why? What are the underlying principles and rationale that guide the answers to the previous 2 questions? Why is it like this? Now, that why question is a very interesting one because it doesn't always mean that it's going to be a good thing. So sometimes people have this thing, oh, we don't really have an architecture. No, you have an architecture. It might not be very good, but it's still an architecture. I've had that kind of response where somebody complained at me for a few minutes, oh, we got this, and then when you work in this system, it uses that technology, and then the COBOL programmers did that, and so we got that layer, and we've got, yeah, so we don't really have an architecture. And I said, everything you've just complained about in the last 5 minutes, those are all the hard things. That's the shape of your system. That is your architecture. But it's not very good. Nobody said architecture had to be good. Dear God, have you seen some of the buildings that people created in the 1960s and 70s? It's still architecture. It doesn't make it not architecture. It just means we have a value judgment on it. So this is important, that that's another thing. Architecture is the things we complain about. That's not a bad definition either. But this is the idea. Sometimes the rationale is not rational. Sometimes the way things are is arbitrary. Why have we suddenly got a cloud strategy for what we do when it doesn't make sense for what we do? Oh, because the CTO read an article over the weekend and now we're all doing this. Oh, okay. Yeah, I had this with a company. Beginning of last year, we were supposed to do some work. I'd done some work from the previous summer, just a couple of talks, but we were going to go much deeper into their Java stuff. So I get in touch with them in the new year. Yeah, we've spent a few years migrating to Java. The guy emailed me back. But our CTO has decided that's no longer our strategy. He must have spoken to somebody or had lunch with somebody or played golf with somebody, with appropriate social distancing at that point. So we're doing something else, and it's just like you guys have just spent years, because I actually did something for them in the 2000s. I know the history of this company. It's just like you've just spent years migrating your developers to this, and you're still not fully there. And now you're not going to do it anymore and you're going to do something else. It's just like because somebody came up with an arbitrary decision. Now, that's not necessarily a good decision. It's not necessarily well informed, but damn, it's going to shape everything that they do. So the way things are is not always a good reason. Sometimes there's just a reason. But sometimes there is an intentional rationale. We did this for memory constraint. We did this for bandwidth reasons. We did this because we had to have backward compatibility. We did it. There's always a reason why we do things. Sometimes we're not immediately aware of it. So there's this. This also defines the paradigm and the architectural style of what we're doing, the shape of it in that sense, the way things, the form of it, if you like. But this also emphasizes the structural view. Structural, intentional, or rationale-based. So let's talk about this idea of dependencies and connections, because they are one of the things that characterize why an architecture works, but also where the resistance comes from, why things can be hard. So let me just check on something. Yeah, that's good. Cool. So this is a quote from Parnas when talking about modularity in 1971. Modularity, in the most general form of the term module. I know some languages have decided to claim the term module for themselves in a very particular way. So this means that Java people can no longer talk to JavaScript people. Not that they ever did, but there we go. But when Java talks about module, it means actually something fundamentally different to when JavaScript talks about module. The term module in its most general sense is, here is a chunk of code that has a boundary. It's got an inside and an outside. It's a public part and a non-public part, and it gathers things together. And it may be quite small. It may be actually quite large. It may also correspond to runtime deployment, what is conventionally called a component. But modularity in its most general sense. But notice what he says. The connections between modules are the assumptions which the modules make about each other. Now, when we look at code and we trace through in an IDE, or we sketch out things, we normally choose the easy dependencies. In other words, here, we're calling this. Oh, okay, so there's clearly a dependency between this thing. This uses this. Oh, that's great. But also, there are cases where we assume things. I am calling this, okay, You're single-threaded, that thing's single-threaded. This is good. Notice the assumption there. We never said, oh, by the way, they're both single-threaded. In a single-threaded program, you'd never say that. But suddenly somebody decides to launch a bunch of threads across the code base. And this happens for a number of reasons. One company I visited, oh yeah, one of our guys had just been on a training course and learned about threads, so now we have threads. And that caused no end of problems. But the point there is the assumptions. When I use that other piece of code, what am I assuming about exception safety and thread safety? Assumptions are slightly invisible. They're quite annoying because you cannot list them. You can never say, here are my assumptions. The best you can ever do is, here are my known assumptions so far. And when I discover something else, how do you discover an assumption? You don't discover an assumption by sitting and pontificating and meditating hard. That may reveal something. Probably why am I working in this programming language? But, you know, what you find is that an assumption is something you learn in retrospect. You learn by contradiction. It's a piece of knowledge you have but don't know you have until you discover that it's wrong. Okay? So in other words, somebody says or shows something and you go, oh, but I'd assumed that. At that point you know you have an assumption. You never knew that before, but when somebody shows you what the customer actually wants or how that framework actually works, you've discovered that you were wrong, which means you had an assumption. Our assumptions are normally uncovered a little bit like walking in a dark room barefoot with Lego bricks on the floor. You know that there are Lego bricks there, you just don't know where they are. Okay? And then you discover them the hard way. It's, that was an assumption. Yeah, feel free to say that next time you step on a Lego brick. But there's a point here. It means sometimes it's about the way things work, and we don't realize the way they work. So if somebody says, oh yeah, send us dates. So I had this with a company in Belgium years ago. We store everything in using dates, dates in string format. I said, well, that's unconventional. Databases do actually have date time fields, but no, that's cool. And then I started seeing the code. Oh, what the hell's going on here? You see, I had an assumption. If you're going to store dates in strings, then you're going to use ISO 8601 format, because anything else would be stupid. In other words, 4-digit year dash 2-digit month dash 2-digit day. No, they were using American date ordering in Belgium. I mean, I know Belgium's kind of a bit of a mixed up country, but come on, guys. That's just the craziest ordering in the craziest place. That my assumption was, well, of course you're using ISO 8601 because anything else would be stupid. You would have absolutely no advantage and you'd always have to work around it and your queries would be complex and your code would be Yes, that's exactly what we've done. Oh, why didn't you stop doing that? Well, because we've always done it that way. Yeah. But if you changed it, all of your code would be easier. And so would all your relationships with all your partner companies. Oh yeah, but that would involve change. Now here we hit another obstacle. The nature of human nature, yeah. So let's look at the kind of invisibility and subtlety of some of our dependencies. So let's call this boundary the system that we're working on. What we think of as our system. This is a subsystem. Maybe it's a package, maybe it's an assembly. I don't really care about it. It's bigger than just a bunch of classes. Okay, it's big enough that I can meaningfully talk about it. Now, within our own code base, we have dependencies on other packages, other subsystems, and we know about those. Maybe those are in our team, maybe those are not. But we recognize those as architecturally separate in some way. There is a public-private. There is something there. There is some boundary there. But we recognize that this is inside our system. So the key thing here is this is all code in one sense that we own collectively, although I might own that or our center of attention is there. And this is what we often talk about when we talk about dependencies, that immediate nearby view. But then scratch the surface a bit and you go, well, actually, these depend on other things. It's code that you don't own. And that also has dependencies. Now, the funny thing here, and if you're a JavaScript programmer, this is mostly how you program. You depend on NPM. And NPM is a rat's nest of dependencies. But here's the thing, this could be Maven working for you as well. There's lots of different, and people often say, well, oh, okay, that's outside our control, and we don't need to worry about that. I have some very bad news for you. You do need to worry about it because it's part of your architecture. I remember saying this to someone who said, no, that's all part of your architecture. What, you mean we have to know about those? Yes. And the reason the person was looking worried is because I had no idea. How does your system build? I don't know. The scripts do it. What do you depend on? We don't know. So basically, the security of your system, you don't know it. Oh no, our system's secure, but you just told me you don't know how your system is built. How can you, these two statements don't live in the same sentence. Okay? There's a problem here, and that means you're also vulnerable to things that are outside of your control. It's really important. This is under your control. As humans, we like the things that are, oh, this is our architecture. Yeah, your architecture is all the things you don't control. And there's a lot of them. Now, so, I'm going to take you back to 2016. Does anybody remember LeftPad? Okay, only a handful of you. Right. The LeftPad incident. The LeftPad incident was interesting because it was based on some open source code that was entirely unnecessary. And what I mean by unnecessary is that it was just a simple string padding function. I would not import another library to do that. This is really basic stuff. Every time you take on a dependency, you take on risk. But that's not always bad. Sometimes you take on benefit as well. I mean, I don't really want to go and recreate, unless my business is actually creating databases or creating web servers, I don't want to have to recreate those. So in other words, we take on a dependency. It means we get a benefit, but we also get a risk, a liability. And we are exposed to that risk. The question is, we hope that the benefit outweighs the liability. Otherwise, what's the point of it? So am I going to import a 10-line function to pad a string with zeros? Just because JavaScript can't be bothered to do it itself. Well, it turns out that you actually only need about 3 or 4 lines, and these days in modern JavaScript, as a result of this, you only need 1 line. But what happened is there was a disagreement over licensing. And the author of this particular library, LeftPad, pulled the library, which they're entitled to do. Open source is a gift culture. If somebody says, "Oh, by the way, we don't like we're going to change the terms and conditions under which you contributed," somebody's well within their rights to take that back. They don't owe anybody anything. And when they pulled it from npm, suddenly a lot of websites stopped working because it was a transitive dependency. People didn't know that they depended on LeftPad. In other words, they were not managing their dependencies. Sometimes people think managing your dependencies just means having a list of them or having a kind of a dependency manager tool. That's not managing your dependencies. Managing your dependencies means that when somebody says, "Why are we depending on LeftPad?" you have an answer. Oh, because we're using this library. This library gives us benefit, but yes, that is a liability. Why are you using Left? In other words, you're able to account for everything. It's accountability. And therefore, you have a good assessment of the risk. And if somebody else pulls that, then you're able to say, yeah, we understood this risk. We knew it was coming. Okay? Oh, now it gets interesting. It was already interesting enough, but now it really gets interesting. Because it turns out that you depend on your platform. And your platform constitutes a number of things. Programming languages, operating systems, middleware, services, licenses. Oh, licenses. Things that you didn't know you depended on. Let me think. When was it? 2018? 2019? I don't know. The pandemic blurs all numbers. But a couple of years back, just coming into Christmas, in the UK, there was a major outage on the one of the largest mobile networks in the country, O2. Major outage, which finally, by accidents of history, my wife and I are on different networks. So it allowed me to be smug about her choice because she was on O2. It's just like, oh, that's not working for me. But most of the country could not access their mobile internet or anything. And eventually it was traced to an expired license on an Ericsson server, I think it was. Yeah. You depend on those. You depend on your operating systems. People are, oh no, but we were insulated from our operating systems. No, you're not. You run on an operating system. The degree to which you depend on it, that's interesting. Can you take your code and have it run on another operating system just like? If so, well done. That you've got relatively frictionless flow. That's not architectural. But you might have accidental dependencies. So one of the things that I'm known for is people send me failure screens, failure messages. A lot of these are from versions of Windows that are no longer in support. It's very interesting realizing how much of the stuff in the public space is on unsupported operating systems. That has security implications as well. So the point there is you depend on these things. You depend on the programming languages that you use. I spoke to one team and I said, okay, you've drawn me this beautiful box diagram, but nowhere have you mentioned programming languages. Oh yeah, those are just implementation details. Are they? Okay, let's list them. C++, Java, Python. What version of Python? This is about 3 or 4 years ago. I said, oh, mostly Python 2. I said, you do know the clock is running down on Python 2. Python 2 is no longer going to be in support pretty soon. You know, all the evolution is happening in Python 3. All the support is happening in Python 3. Why are you still on Python 2? You know, it's not like they didn't tell you that this was going to happen. Oh, well, we are using Python 2 because there is a library that we depend on. Ah, so you depend on a library, and because you do that, that library is now telling you that you can't use Python 3. In English, there is a phrase about the tail wagging the dog. Yeah, in other words, you didn't choose your architecture. Something else is choosing it for you. You can't migrate to Python 3 because of one library that you're using. This is why you need to understand your dependencies. Okay? We also had it, we went through the C++ and the Java. Why are you still on this version? What is your plans to migrate to this version? Okay? So these are the invisible things. They are like the air that you breathe. You don't get up in the morning and think, oh, okay, there's oxygen. Phew, that was a relief. That was good. That's my dependency. Yeah, dependency 1. Next, breakfast. Ah, no, caffeine, then breakfast. Yeah. Okay, you know, you don't sit there thinking oxygen is the first order of the day because it's so available, you forget that it's there. A lot of this stuff is there as well, until it's not. Then you have the other dependencies, the very market that you work in. That comes with governance rules. Let's understand, for example, so in other words, if there is no market, if you have no customers, guess what? Your development life is easy. At least briefly until your company runs out of money. But the point there is that will shape your work. The rules of that market will also shape your work. If there's governance, then that is going to shape your work. Because sometimes people that, you know, so where does governance fit in terms of requirements? It's not customer requirements, it's market requirements. In other words, if you are going to play in that market, that's, you know, if you're going to, let's talk about medical systems. Medical systems, there's a whole load of legislation for safety reasons. That's not a customer requirement. That's a market requirement. If you are to participate in that game, you have to play by these rules. The customer doesn't have to tell you that there are those rules. That's not their requirement. It's a requirement that they are living inside of there as well. So these are all the things that your code and the shape of your system depends on. And as Adrian Collier points out, it's often not the direct dependencies of your project that bite you, but the dependencies of your dependencies. You need to understand what those are. Now, while we're talking about that, let's have a look at this kind of idea of the weight of dependencies that we might be dealing with. And also to make a case for what I was saying earlier about the scale. Is it possible we close that door a bit? I know that oxygen is kind of... Yeah, well, when you pass out, then, you know, when everybody's passed out, we'll know that we reached that point. I mean, I'm referring to oxygen a lot here. So, okay, so what I want to do to get a sense of the idea of architecture and scale is to understand something else. Let us... So, there's a nice little box there. And a far bigger box over here. If one presents a box diagram, the clear idea is, well, that's clearly more architectural than the thing on the left, because the thing on the left is kind of tiny, yeah? Okay. So we might have that kind of simple perception. Okay. Well, let's start drawing some, what I'm going to do is I'm going to draw some people on, because this is the thing, this is the thing that people always forget. If you want to understand a system where people work, you need to draw the people on. People never draw people on diagrams, except maybe the customer or the user. They never draw the developers. That's really, I think it's a huge oversight. Somehow, oh yes, the architecture is built by developers for developers. Developers inhabit it, but we don't draw them on. They're like invisible. You know, it's a neutron bomb in our system. So there is a point here. Why am I drawing the developers on? Okay, so at the moment, it looks like the thing on the left is, okay, we've got a couple of developers or some team, we've got another team over here. Looks like these guys have less of a problem to deal with for changes than the folks on the right. Whatever is in that box, whatever I mean by that, I'm being very open about what this could mean. I don't want to close our options. There's our dependency. Okay. Okay, now, this is where it gets interesting, because we start realizing that the ability to change something is not just about the size of the thing, but the size of the dependencies of the thing. And so let's talk about this in terms of other people affected. And this is kind of an important thing, because what we're realizing is the dependency set on the left-hand side is huge. The size of the making a change to this has massive implications that this simply does not have. So yeah, the box here is bigger, it contains more stuff, whatever that stuff is, whatever that functionality is. So we might say, oh, making a change over here is a bigger thing, but actually you're going to need much more political will and insight over here. The dependency set is massive. And we can even actually relate another concept here, which I term organizational distance, because I don't have a better term for it. Org distance. These might be in the same organization but different teams. I can communicate with them, I can influence them, and I probably know that they're using this. So my ability to change this, although it's not as immediate as it is with my own team, let's just say that they're using different repositories or they have different objectives and deadlines. I can't immediately just do a change, but I can make that change. I can say, look, we're going to retire this interface. I know you guys are using this, but another couple of weeks and I can do point to point. I can actually know the people. But as the organization gets larger and larger, as the distance, these are people in other companies perhaps. Open source is really interesting because you're at the largest, in fact I had this with one library I contributed to. It wasn't a very big piece of code, but I suddenly realized the implications of, I have no idea who uses this, but I know lots of people do. In the particular library that it was contained, it was one of the top 10 libraries. It's only a few hundred lines of code, but if you screw that up, people are going to be affected. That's the only reason they'll ever know your name, Kevlin. That's the other definition of architecture. If you make a change, how loud is the shouting? Yeah, the louder the shouting. Oh yeah, that was architectural. I actually gave, and that's the important point. It means that the size of the thing can be deceptive. And all too often when we say, oh, it's the big box diagram, the architecture, the PowerPoint architecture, they're too busy looking at the size of the boxes instead of like, yeah, but who's using them? That's the bit that makes it hard or easy. This could be trivial to change in one sense. I gave the example this morning in my refactoring talk. Tomorrow, Oracle could turn around and rename clonable interface. That would be trivial for them. It takes one developer, rename, done. Meanwhile, the rest of the world collapses. The point there is that it turns out that that's all of that. Oh, so you mean that naming is actually architectural? Well, not always. If I've got a local variable inside a method, then I can rename that freely. But the more exposure, if you like, this adds mass to it. This makes it heavier. Each one of these is potentially a chain. And these are long chains, some of these. So this is one of the most important things when you want to understand the shape and the connections in your system. You can't just look at the things that are right there. You have to start taking a step back and saying, well, who else uses this? But also, you're in the same position. We use somebody else's. That was the previous diagram. So the architectural mass of something is not just the thing. It is the set of this dependency set as well. So you need to look very, very broadly at this. Now, there's a number of cases where we can actually see how this one plays out. And that can be details about... so yeah, right. So what I'm going to do is we will look at... we will look at a map of Paris. Why are we looking at a map of Paris? Because Paris is beautiful. I mean, who doesn't want to go to Paris? I've just looked out the window. It's raining solidly. Honestly, Paris rain in November is, I'm going to say, better than Lithuanian rain in November. But here, I've got this view. Why am I showing you a picture of Paris? Because this is a big picture view. At this level, we can see the Seine. We can see some of the main routes out. We can see some of the key Tourist sites. Okay, that's cool. That's nice. Very pretty. Can you see the direction of driving? I mean, you know as a matter of general knowledge and expectation that in France they drive on the right. But that's not what I'm asking. I'm not asking what you know. I'm asking what this diagram communicates. Can you see? Can you see that they drive on the right here? Well, it's not visible. Okay, let's zoom in a bit. Right, we are now at a level I can start using this as a walking map. Okay, I can see the metro stations. I can see the fine arrangement of the roads. I've got more details and more sites. Still can't see the direction of driving. Finally we get some arrows. At this point we learn that actually Paris doesn't have a side of the road. It's all one-way roads. But actually, if we look closely, we can see a couple of places where, oh yeah, that's on the right-hand side. Notice we are really zoomed in at this point. Now, why am I showing you this? Because what this is not, the side of driving is a small detail for some people. Oh, that's just a detail. That's not architectural. Okay, change it. Last country in Europe to change side of the road? Sweden, 1967. They took a few days to do it. Yeah, it was done gradually. It was a big deal. If you tried to do that in Sweden today, you couldn't do it. Because Sweden's population is larger. Its dependency on the car is far larger. Back in the 1960s, there were not a lot of cars compared with today. It turns out that that was a kind of sweet spot. That was kind of the last, or almost the last opportunity. Certainly by the time you hit the 1980s, it's like, no, the dependency on the car has just taken off. Population density has taken off. It is not trivial to change that. You are not just changing the side that people drive on, you are changing where all the signs are. You are changing all the public vehicles. Because the way that buses work is you're supposed to deliver human beings alive to the pavement rather than into oncoming traffic. It's a small detail, but, you know, hey. If you go to Stockholm, you can actually see that the underground station, if you look at the underground station, it still is on the left because it's not affected effectively. But if you actually go, oh, yeah, that's kind of interesting. Now, the reason I'm talking about this is because I've already talked once about the invisibility of things. But this, for me, is things like this. And there's, in other words, I'm talking about execution model. Intentionally, I've omitted stuff because what I want to do is say, this is fundamental. I've joked about, you know, adding threads to a code base that doesn't have them. But this is actually really deep. If somebody says, oh, we're going to switch to using an actor-based model, or we're going to take this code that uses one particular simple approach to polling messages, we're going to make it event-driven. That is not a small change. And I've had people tell me, oh yeah, just this kind of stuff is an implementation detail. No, it's not, because you've just rearranged the nature of time. You've just messed with the physics of your system. There is really nothing more fundamental. Forget oxygen, this is gravity and time. Okay? I refer you to Interstellar and other things, but there's the point. You're doing something fundamental. You are changing the nature of time for your system. If your time is organized by coroutines, that is fundamentally different to organizing your time by threads. If your time is organized by events and handled in a single-threaded manner, that's actually different to interrupt-driven code. In other words, all of these are arrangements of time. These are not implementation details. They may be expressed through a library, but they are actually fundamental. And that is why it's so hard to take a code base that has one very strong view of time and mix it with another code base that has a different view of time. My earliest experience of this was taking a code base that we had developed that was resolutely single-threaded but event-driven. Okay? And I think it did a reasonable job of that. But then I was asked to integrate another library as a supplier of events to our system. But this library was multi-threaded. It was thread hot. And I was asked to do an assessment. My assessment, after about a week of looking through our code and their code and how they do it, I said, there is no way that we can ever do this and guarantee that we have no bugs. It will always be hard work. It will always be unsafe to some degree. I mean, maybe we could get it right, but this is a game of probabilities. And I don't think we have a good chance here. So what did I do? We created a separate process where things were integrated, and that was the job of this process. It was to translate between two worlds. And the only way we could do it was with a hard process boundary. That was the safest way to do it. The only way to unify time was isolate it in a bubble over there. And we'll pretend that that bubble is giving us our nice single-threaded style events, and on the other side, they're getting multi-threaded things, and that's fine, we're all happy. But we will not mix, we will not cross the streams. These are two fundamentally different styles of composition. So this is really important, and comes back to developers. Because details count. And one of the most frustrating phone calls I ever had was with a client. It was in India, and I had the architects on the phone, and they said, yeah, can you recommend any thread-safe libraries? And I said, well, okay, what do you mean by thread-safe? I mean, all libraries are thread-safe. It's just that some of them, you only want to run one, they're only safe for one thread. Yeah? But I've also seen libraries that are safe for 0 threads, honestly. I wouldn't trust my code to walk through that. The point there is thread safety is not an absolute. You need to define what you mean by that. There are different ideas of this. So I said that the problem is, so what is your threading model? You're the architects. How have you defined threading? Oh, well, we thought that was an implementation detail and we left it to the developers. How's that working out for you? Well, it turns out the developers have all got different ideas about how to do threads, and now we seem to have a lot of mess and a lot of bugs. And I said, right, you think that adding a library is going to solve that. You are now in a people problem space. This is to do with people. And it's to do with the fact that you didn't... First of all, I wasn't telling them off, although I was. It's just like, threading is not a detail. Process partitioning is not a detail. These are all fundamental. You're defining the nature of time for your system. And you can't just let people do local decisions on that and expect everyone to agree. Maybe one of these is really good and everybody could copy it. But that's the idea, is that this one has gone under the radar, and now you have this mishmash architecture that is in need of caffeine. So let us do that. Caffeine and oxygen. We've done the gravity. Let's go back to caffeine and oxygen. So what we're going to do here is we are going to take a break, and I'm also going to try to find Narnia. Okay, there we go. Okay, so this is a cuckoo time. It's kind of cute. It comes up with random stuff. But I will see you back here in 15 minutes.
I'm saving the coral reefs using underwater AI.
I'm helping food get to those in need, fast.
I am reducing waste in the global fashion industry.
I'm helping make live theatre more accessible for the hearing impaired.
I'm securing our future.
I'm disrupting the world with quantum computing.
count down so that it's all kind of like, you know. Awesome. Right. Okay.
I'll put it there, okay?
So this is one of my favorite quotes from the early 1990s. Edward Berard. Walking on water and developing software from a specification are easy if both are frozen. And there's kind of some really interesting thoughts about that one in terms of how you can relate to it. But one of the things that we find is that this causes us to think a little bit more about the nature of development process. Now, I'm going to talk about process. A lot of people think, oh, well, architecture is somehow different. That is one of the greatest problems we have ever had, is the separation of the idea of, oh, you don't need to worry about development process if you're doing architecture. It's just like, well, no. First of all, everybody's doing architecture because even the smallest decisions that you make, or what you think of as small, can have huge implications in future. When somebody chooses a 32-bit representation for something, and it later turns out a 64-bit representation would have been better and more appropriate, but you've now published it in an API, you have that exact problem of the renaming and all the rest of it. It's like, oh yeah, everybody's kind of dependent on this being an int, a 32-bit. In other words, we published an interface, and now people implement. Now, if you take an interface and you go, int to long, then that suddenly breaks every single piece of code that was ever written against that interface. And so it's, okay, so we're going to have to be very careful about how we do that. The way that you build things changes what you can build. And what you can build changes the way that you will then change it in future. In other words, there's this intimate relationship between architecture and development process, which when you look at it like that, it's not really surprising, but is important. So microservices as an architectural approach, a lot of reasons that people do microservices, most of them are completely incorrect. In other words, sometimes people say, oh, we do microservices so that we can isolate our work from other teams' work. Yeah, no, we solved that problem a few decades ago. Every single new paradigm that comes along says the same thing. They're all based on modularity. The minute you go microservices, you're creating a distributed system. If you didn't have distribution before, or you didn't have distribution inside your system as opposed beyond just a client-server relationship, you have now introduced new points of failure, new points of complexity, new points of latency. You've made it harder. What's the benefit? Why would you separate such things? You would separate it because of separate deployment. And scalability. Right, now we're actually getting to the bits that actually matter. So in other words, if you're doing microservices because you're hoping it's going to improve the modularity of your code, don't do that, because if you, to kind of paraphrase Simon Brown, if you can't do modularity without this, what makes you think you can do modularity with it? You already have all of the constructs. It's already a solved problem. So you're inviting complexity there. But the main reason that we do these things is because it changes the deployment architecture. In other words, the way that you can deploy changes when you use microservices in a way that is not as accessible if you use a traditional component model. That's one of the big things. And scaling. Okay. So that's the real value. So so in other words, if you didn't have an idea of, we have a deployment approach, in other words, our deployment historically fell outside architecture, unfortunately, because it's like, well, that's not my problem. It turns out it is. But more importantly, everybody is influencing these things. If you have somebody who is a project manager and they change your budget or they change your team, they have just changed your architecture. If somebody says, you got 6 months for this, and somebody else says you have 12 months, you're going to get a different architecture. So this is a rather interesting, because if you think that all of the decisions go through a person called architect, I have bad news for you. It's everyone. Everyone who has any involvement in what you're building can ultimately influence the things that become significant. Because, of course, if I gave you 6 months, the thing you built would look different to 12 months. If I said we're going to release every day, of course the thing is going to look different to if I said, we'll do quarterly releases. You are going to end up with a fundamentally different shape of thing. The way that you build will change what you build and how you build it. So let's go back to a kind of traditional simple view and understand it, and where architecture fits in it. And this is entirely rational. First of all, we understand what we're trying to build. then we make decisions about how we're going to build it in terms of the form. We take all the, by the way, yeah, we take all the significant design decisions here. This is where the architecture happens, yeah? And then we actually code it. Well, sometimes people go, oh, that's just implementation details. Oh, I love it when people do that. It's just that, yeah, what exactly did you think software was? It's all about details. You know, let's put it another way. Nothing exists until this point. Nothing real. And the stuff that exists here is not particularly real either, but it's even less real here. And you know what? I can always make this work. I can wave my hands and I can do things on a whiteboard. Whiteboards never crash. Well, actually, that's not true. I have had whiteboard crash. The diagrams don't crash. Bubbles don't crash. Boxes don't crash. I can always make it work. I can always run it on the VM of my mind and the performance is awesome. You can always make it work if it's just a diagram and it's just text. I even actually intentionally did this with a group where we were trying to introduce an agile process and we had the difficulty of a meeting with the client. And I was working with the business analysts and they were not going to give us, they needed a meeting. They wanted to sign off on a written specification. But the meeting to resolve something that was fundamental to what we were building, in other words, it was to do with pricing, they wanted to have the meeting to do with pricing next week, but by the end of the week, they wanted to have signed off on the specification. Again, I invoked time machines. There was a problem here. But what I eventually did through a careful piece of wordcraft was I created 2 sentences that were not wrong about the pricing. They were so abstract and vague that they were correct. And you could sign off on them. But they said nothing because they lacked detail. Software development is a progression of the abstract to the concrete. It is when you write code, you have committed to detail that previously you may not have realized you needed. At this point, the rubber hits the road. At this point, you get the feedback. Oh, and by the way, we want to check we did it right. So this looks great on paper. It looks great. It's easy to explain because all 4 activities, and indeed we could have others. I could put deployment, I could put all kinds of other requirements, elements in here, but I'm just going to keep it down to 4. Really simple. Understand what you're going to build, decide what you're going to build it, check you built the right thing in the right way. Okay? There's nothing wrong with this. What we have, though, is an assumption that is very subtle, that these occur in this order distinctly for large-scale things. That is the assumption. We've done 2 things that are right. We've identified the activities, and we've identified that time is partitioned. The problem we've done is we put one activity per box. That is the thing that is wrong. So what do we do when this doesn't work out? Well, clearly we didn't spend enough time analyzing and designing up front. And you know that this is not what happens. Eventually this line moves, or we just get rid of the testing phase. Oh, the customer's testing. Oh, this is this beta testing. It's like, yeah. Now the thing is, what I find interesting about this is that the original intent of this approach, it's very rational. It's to try and reduce risk. It's to try and address the unknown and deal with the things that we don't know by preparation. The problem is that we actually put off the point at which we make our discoveries. In other words, this is not an approach for reducing risk. This is an approach for increasing risk. It has exactly the opposite effect. Because the point, if this is your delivery point, the point at which you find out moves closer and closer to the end. In other words, you increase the risk. You have exactly the opposite intent, opposite from the original intent. And you don't need a large team, a large project, and a big commitment to see that this doesn't work. I've done this in less than a week with people. And what was absolutely fascinating is one particular instance I remember. At the end of the week, there was one particular team. I had teams of 4. And I got them to develop stuff through the week, kind of coaching them as they went. But there was one team that just was not. No, we decided we wouldn't test because that was taking too much time. And I also got all the teams to say, they gave a presentation at the end. And one of the things I got them to do is, what would you do differently next time? And this particular team said, well, we didn't have enough time to do all of this stuff. and we tried really, really hard. We spent a lot of time in the early part of the week, even though we spoke about agile development. I think I must have slept through that. We talked about all these things. They did exactly the opposite of what I told them to do. But I think it's always instructive. And one of the best things they said is, oh yeah, next time we would spend longer at the beginning coming up with analysis and design. And I said, you do know that the problem description fits on less than one side of A4, and that description did not change through the week. And that everybody else, why do you think that spending longer on one piece of paper would have made any difference? The difference is when you started to build it, you made discoveries. That's where you find the detail. That's where you reveal the assumptions. That's where you get the feedback about, oh, I didn't realize this. And that's where you discover whether or not you can work as a team. That's actually the first thing I always tell people. Your greatest risk is, can you work together as a team? And people always ignore that. In the first sprint, they always go, yeah, we're going to put half the backlog into the first sprint because it's so easy to code. And then it's just like, oh, but working with other people turns out we need to coordinate and talk to each other, and we don't all have the same ideas. And we didn't know that. Yeah, that's why I said always plan for less at the beginning. But what I also find interesting is some of the decisions that they took for such a toy problem. People were creating manager monsters everywhere. They created an architecture that was a perfect copy of all the problems they already experienced. You don't need years to create problems. It turns out you can do it in just a few days. So there's a point here, and this applies equally well to caching as it does to how we develop. It's expensive to know everything up front. This is the point there is that most of what you're going to discover is on the way, and that's fine. There's nothing wrong with that. As a human being, you work with incomplete knowledge. You do this every single day when you get up. You are remarkably successful at working with incomplete knowledge. That is what humans are good at. You get up, you didn't know what this was going to be like, now you've got a better idea. But you still came to it, you already had an idea. You probably made decisions about other talks today that you didn't know when you woke up. And you are still functioning brilliantly. Humans work with incomplete knowledge incredibly well. What is our failure mode? Our failure mode is when we think we know everything. When we know that we don't know everything, we operate in that way. And we say, oh, there's new things that come. I've got some ideas. I've got possibilities. And there are also things I don't know about that I'm going to discover, and I may change my mind. The minute when you recognize, I don't know everything, I'm good. And you are really good at working with incomplete knowledge. The biggest problem is we fool ourselves with, oh no, we know everything now. We have the plan, and it will be like this. Now you're inviting failure, because the universe doesn't agree with you. Also, there's a certain amount of self-awareness here. Quote from Nassim Taleb's book, Fooled by Randomness. People overvalue their knowledge and underestimate the probability of their being wrong. What's the probability that all of the, I've had people say, oh no, but we know these architecture decisions. And I said, yeah, I know. Nobody's going to say they didn't know. We've done this, we've added this. And I said, it's really complex. Yeah, but this is going to happen. Is it? Do you know that? Or do you just believe that really strongly? A strong belief is not the same as knowledge. Knowledge is something you can prove. The problem is that a lot of knowledge is in the future. I believe something, that's great. We all have beliefs. But what are we going to do about it? And this was really interesting. With one team, they had interfaces all over the place. And I kept looking at the interfaces, and they were all implemented with empty methods. That's not what we were looking at. And it was to do with their persistence model, from what I could tell. And I said, well, why have you got this here? Because I'm noticing these are there any implementations of these methods? There's nothing wrong with having an empty method implementation. But if all the implementations are empty, I know a much easier way of doing that. There are much easier ways of doing nothing in code than actually having 50 different classes implement nothing. I said, what's this doing here? Oh, we're saving time. For what? From the future. Right. But what's going on here? We might persist this to disk in a way that's different for local caching rather than the way that we're currently building the data model. Because occasionally our server crashes and it takes a long time to reconstruct the in-memory data model because we populate the object model by talking to other servers. But maybe if we cached it on disk and pulled it back into memory, okay. Is that actually a requirement? No, but we thought we might have it. Okay, but you do know that currently no code implements this, so you haven't actually saved any time. And you also know, by the way, having implemented stuff like this, that you've got the interfaces completely wrong. You're missing certain dependencies. because you haven't actually written any code that, oh yeah, you're right. We haven't got any dependencies on where do we save and load from? Oh yeah, we haven't got a target. Completely forgot about that. So are you suggesting, Kevlin, that we had an argument? No, I'm suggesting you delete all of these interfaces because you have no idea not only what the requirement is, but even if it exists. And you haven't even got any example code to show me how it works. We have another name for example code, by the way. It's called tests. It's example code with assertions. I said, you haven't written any tests for this. They eventually became one of the most test-driven teams I've ever worked with, but not at this point. And that was the interesting thing. The path into the future was by deleting all of the interfaces and empty methods. In other words, the way you go into the future is you streamline. You don't add things. How do we make the airplane go faster? Oh, I tell you what, let's add lots of stuff. No, you reshape it and you throw things out. You make things lighter. You change the form of it. Okay, you don't add weight. So it turns out that was the whole thing. But you talk to a lot of people and say, oh, no, we know we need this. No, you don't. You believe you need that. Okay, so how do we solve this problem? Well, we do something like this. We do this all the time. Okay? All the time. Nice and simple, okay? But actually, here's the most important bit. Don't fall into the PowerPoint trap of making everything line up. The whole point of this is that you don't know the future. You're going to change the direction. That's the idea, is course adjustment. Oh, okay, it's slightly different. And that may be awareness of your own knowledge, but it may also be awareness, new knowledge that comes in from outside. It may be requirements changes. But most people, when they talk about change, they think it comes from outside. Most change actually happens on the inside. It's your knowledge that changes. And in fact, let's actually let's talk about that, because that idea of the knowledge changing is fundamental and tells us the challenges that we have when we start thinking about those significant decisions. So let's draw up so the horizontal axis is time. And what I'm going to do here is define a line. I'm going to call knowledge. Obviously, whatever we're talking about, that could be, I could be showing you a day, I could be showing you a release cycle. It doesn't really matter. But the idea is that at the beginning of whatever it is that you're doing, you have a certain amount of knowledge. By the end, you have a greater amount of knowledge. Okay, that's just the way it is. Now, sometimes I get people saying, yeah, but sometimes you end up feeling like you know far less than when you started. That's different. That's to do with the fact that you become aware that the horizon is moving away. The more that you know, you suddenly realize there's more that you don't know. It doesn't mean that your knowledge has decreased. Your relative knowledge has. In other words, your understanding of now what you don't know has changed in proportion. You realize after a while, I know nothing. Okay, that's different. That's a relative thing. The absolute knowledge that you have has increased and increases with time. Of course, it's not a straight line, and I haven't said anything about the scale of the axis and all the rest of it. This is just suggestive. So there's an interesting thing here. If you make all the architectural decisions early, you're making them during the period of least knowledge or greatest ignorance. It doesn't really make sense to, well, we don't know anything, let's make all the big decisions now. Can I suggest that's not the best option? Sometimes you need to structure your decisions differently. And while it's something that, you find this in lean development, it's called options thinking, last responsible moment, all this kind of stuff. And I had this with a team. They'd taken over a code base. It wasn't theirs. There was a lot of database stuff in it. They didn't really know databases, SQL Server. And they said, Kevlin, we have this particular requirement. How should we do it? And I said, I don't really know databases. So we have a room full of people who don't really know databases and don't really know SQL Server. But Kevlin, what should we do here? And I said, well, we don't know. Well, we were thinking that we would plan it like this. And I said, yeah, but you still don't know. I said, when's your major release for this? And they said, 16 weeks. I said, okay. If SQL Server offers you the features that you need in a way that you need them, how long will that take you to implement? I mean, we're just guessing here. I said, I don't know, a week or two. Okay. If it doesn't, and you have to hand code this How long do you think it'll take? Let's say 5 or 6 weeks. Okay, I said let's call it 8 weeks. So in other words, in 8 weeks' time, you need to make a decision. Because in 8 weeks' time, you will still be able to choose both options. But, and of course, that estimate could change, but I said also in 8 weeks' time, every single person on this team will have 2 months more experience of working with SQL Server. At this point, you will never know less. With this code base, you will never know less than you do today. Okay, over the next 4 months, you will never know less about it than you do today. Now is not the time to make the big decisions. But we're not abandoning responsibility. We're not just saying, oh, I don't know, we'll do it sometime. No, we're actually structuring it. And we might change that date. That date may move forward or back based on our knowledge, but it's constantly under revision. In other words, we can't make that decision now. So we'll take a decision to take a decision. That's the most important thing. The danger is that we always fall into this trap of, it's important, we need to make a decision even if it's wrong. Yeah, that sounds much better on a poster than it does in practice. Sometimes you just need to say, well, let's give ourselves the chance to learn and reach that. By the time we reach 8 weeks, we need to have an answer to this question. Whether that's by prototype or just basic experience or by Google or whatever it is. Maybe we'll ask you a question on Stack Overflow, whatever it is. So the point there is that there are some decisions you can probably take. Some decisions that actually, it doesn't matter if they're wrong, and that's fine. But some decisions you might say, I'm going to push that, I'm going to punt that decision into the future. But I'm not going to do so recklessly and say, I don't know, sometime in the future. We're going to say, okay, where's the most likely, about there, 8 weeks' time. Let's revisit this, unless we have other calls to. This is the simplest piece of planning that people overlook about this. Okay, now, I want to put this against another line. These are your options or opportunities. As time progresses, you can exercise your options, your opportunities, the ability to do anything. Let's work back. If this is our magic moment at the point of release or the point of whatever we are talking about in terms of our life cycle, this is the end of the day or the end of the year, whatever it is, whatever scale we're looking at that moment, you have precisely no time within this time scale to do anything different to what you are doing. You have no options to do that. And that's the whole point, is your options close down as time goes by. They start disappearing. Your ability to do it, at the beginning, you can do anything you want. By the end, you cannot do anything different. But you'll see here is the paradox of development. Because the point of greatest knowledge is the point of least opportunity to actually use that knowledge. But all is not lost. This is what every development process tries to deal with, and they have different philosophies. We can't change the fact that the basic form of these is true, but we can change the basic shape. In other words, let's get the right pen color. What you want to choose is a development process that maximizes the rate of knowledge acquisition early on. And also keeps your options open for as long as possible. They still drop to 0. Actually, let's redraw that. They still drop. But the idea is we keep them alive for a bit longer. Now, what keeps your options open? This is an interesting thought. Well, funnily enough, as developers, you already know the answer. Loose coupling. All this stuff people talk about, loose coupling, high cohesion, all that kind of stuff. It sounds very abstract, but that's why. Don't depend on the things that might change or you're not sure about. Hey, we have no idea if this is the right way to do this. I know. Let's strongly couple to the assumptions based on the fact that we have no idea at all. No, don't do that. That's why you have things like levels of indirection and interfaces and other boundaries. Well, you just like, we're really not sure about this one. I'm going to put that at arm's distance. Which database technology are we going to use? I don't know. I know we need persistence of some kind, but let's put that on the other side of a line. I'm not really sure about this, so let's not tightly coupled to it's going to be in some kind of SQL implementation, it's going to be done like this. No. I'm going to put a little bit of distance between me and that. What does that distance mean? That's a degree of freedom. Or put another way, it gives you the comfort of being wrong and not having severe consequences from it. In other words, the cost of being wrong is much, much less. You're able to change things. It doesn't mean nothing will change. It just means that the degree of coupling to that. So I'm often surprised when I go to code bases and you kind of see somebody say, oh yeah, we're using the UI framework, and then you're suddenly in non-UI code. Why are we depending on that? Oh, well, because we're using that. Oh, okay, so if somebody changes the UI framework, then that means that all of your business logic that happens to use extra little features of the UI framework in the business logic, you have to change that. Oh, but we're not going to change the UI framework. That's not what I asked. What if you do change it? How do you know that you won't? Oh, but we won't. Everybody says that. They're always wrong. This is the problem. They couple to the things they shouldn't do. And so therefore, there's a little bit, use your uncertainty to help guide you. We're not sure about that. Okay, let's loosen the coupling on that. We don't know enough about it at this point. That is also the same here as keep your options open. Okay, this is the simple stuff of encapsulation at the code level. Oh, so simple example of encapsulation. How do you represent a date? I don't mean that in terms of partner and Tinder swipes and all the rest of it. I mean, how do you represent a date? You know, give me some ways I might represent a date. I'm going to say, as a string using US ordering is a particularly bad one, but that is a valid answer. It's just not a very good one. Give me some other ways. Sorry? Oh, yeah. Other options? Timestamp? Yeah. I can use a timestamp type that already exists. No, but that's the point. Now we can have a discussion about why would we do various things. I can have a number of days since a fixed point. I can use ISO 8601 in string format. I can use ISO 8601 as an integer, which is kind of cute. Oh, let's leave that one to one side. But yeah, but no, you're right. So there's a lot of possibilities here. Do you want to couple to that? Oh no, I know how I use a date, but I don't want to couple to that. That's why we have private in most of our programming languages. It turns out the same is true at a larger level. You know those websites, you probably still come across them. I come across them every now and then that have .aspx in the URL or .php. Why are you publishing your implementation technology in your URL? You have just revealed your implementation. You know, I've had people say, "Oh yeah, our code base is encapsulated." No, it's not. I can tell the language just by looking at your URL. That's a completely unnecessary thing. Oh, but it's the default of the framework. Do not let yourself be driven by defaults. It's your code. Remember those dependencies, the invisible things? Yeah. You always assume that the defaults that somebody else has chosen are wrong for you because they're not you. Okay, never take the defaults without question. So here's the point. You keep the options open by saying, well, yeah, today we're using PHP, but tomorrow I could be using Ruby. Why should other people have to depend on that or know that? That doesn't make any sense. So it's at every single level. The lessons you learned about why we keep the stuff private is exactly the same at every single level. So you loosen the coupling. Is it important that we cut all, imagine a whole code base decides we're going to use an integer to represent the date, and then you change your mind. That's a lot of code to change. So you keep your options open by just closing off the things that you're not sure about. Really simple idea, and yet we don't scale it. So what do we need? We need a process that respects that, but also doesn't do the opposite, which is reduce our options artificially early. This is what plan-driven approaches tend to do. In other words, we're going to have this architecture, yeah, but we don't know that it works. We're going to have it anyway, because it makes us look decisive and certain as if we know what we're talking about. But what you've just done is you've cleared a lot of options that may be useful off the table. It also, unfortunately, decelerates your rate of knowledge acquisition. So you end up learning an awful lot about your architecture's viability as you start implementing it and as you hit the testing phase, because that's how you've structured it. So, to quote the author Neil Gaiman, you have to finish things. That's what you learn from. You learn by finishing things. So architecture, if you want a successful architecture, you need an iterative process. You need something that is going to be iterative and incremental, allows for you to be human, allows, in fact, assumes that you are working with incomplete knowledge, and that knowledge gained will contradict things that you have already implemented. but you need to do that in steps. Otherwise, the cost goes up. If you make big commitments and 18 months later you change your mind, it's going to be a lot more costly than, let's try this. And a month and a half later, you realize that's not the right path. That month and a half is a lot cheaper than that 18 months. Okay? You've got to have that feedback loop. That's absolutely necessary. And that may change very fundamental things. The interesting thing about this, let's talk about architecture. Real architecture. Lovely book, this. 101 Things I Learned in Architecture School. Christmas is coming. I recommend this. Put it on your Christmas list. Everybody will immediately think that you are more sophisticated, more intelligent, and so on. You're not just a software developer. You read, you know stuff. Okay? Lovely book. About half the advice is applicable to any design-based discipline. And there's this lovely observation. Properly gaining control of the design process tends to feel like one is losing control of the design process. Because you're no longer offering a single plan. You are offering a set of possibilities. And you can enumerate those possibilities. So when we look at that, there's a kind of an interesting set of points here. If we start walking through this idea of how do we structure, let me just make a couple of changes here. There we go. So what we end up with is a process that looks like this, that includes all of the aspects that we care about and gives us this kind of incremental structure. But the challenge here is, in terms of increment, is what do we measure that increment in? So let us have a look. Imagine that we have this as our imagined partitioning of our system. So that's a sketch, okay? We say, okay, we're going to develop incrementally. When we say increment, what does that mean? The temptation, there are many temptations, and one of them, our bias as developers, is to assume that the structural units, things like packages, things like classes, the boxes are the units of interest, because they're the units in our language and in our builds. So we say, oh, let's build it by this, you know? Let's do it like that. So we build that. Then we build that. And then we build that. Let's keep things simple here. I've got 6 boxes up here. Let's say that we estimate 1 month for each box. Okay? So far, we are doing exceptionally well. We are 3 months into a 6-month development, and everything's working fine. Right. What's different about B? Yeah, dependency. B now uses something we have already built. Tell me what we might discover. The first thing, we need something else. Oh yeah, I'd forgotten we did. Yeah, we need to rewrite D. There's things wrong in D. There's things missing from D. Then there is the silent dark matter of every software system. The things that we don't use. And it is dark matter, because dark matter is said to shape the forms of the galaxies, yet we cannot see it. What we find is all the dead code. What are you supposed to do with dead code? Delete it. What actually happens to dead code? It remains. And it just sits there, slowly shaping the system in ways that you didn't anticipate. It resides there. So we find that there are things that are missing, things that are not quite right, things that are actually wrong. Depending on how much we've tested, actually there are bugs here. There are things that we need to add. There are things that we should be removing. It turns out that there's a bunch of stuff. But what is interesting is what happens to time. It still takes us 1 month to develop B, but most of the time we're doing B, we're actually doing D. So actually we've probably spent an extra few weeks here. And the problem is that when you treat these as units of delivery, it has a very strange effect. And I saw this in one company when we had a conversation about this. Because I said, but the minute you start doing B, you're going to end up working on D as well. That's not going to be 4 weeks and 1 month. It's going to be 6 weeks to 8 weeks. Because you didn't account for that extra work. And the same is going to be true here and here. One of the most interesting things I saw at a company was they'd say, oh yeah, we solved that problem. Oh yeah, yeah. Well, the architects basically said, once you have finished the subsystem, you're not allowed to go back to it and change it except for bugs. That is an amazing decision, because what you have actually just done is created an architecture-destroying recommendation. Because what will now happen is when I say, oh, there's something missing from D that should go into D, but you're telling me I can't write it in D, where does it go? Yeah. And there's something that's not quite right here. Oh, we better work around it in B. In other words, what you've done is the guideline, although well-intended, is solving an effect rather than a cause. So now what you've done is you've now created a guideline. It's an unmanaged technical debt generator. Well done. Yeah. B is now going to have things that should belong in D. You might as well just mix up all the code while you're there, because all of your design decisions about this is separate from this. The behavior for this naturally lives over here. Yeah. Throw that away because it no longer matters. The behavior for this could go, oh, but you're not allowed to put it in there. Oh, okay. Yeah, we're supposed to be doing some variation of model view controller. Yeah, but all the logic has gone into the view because we finished the model last month. You can see this running. So, in other words, this ended up taking longer. It's based on the idea that you are building, always watch out for the visual metaphors. Software doesn't have an up. The screen has an up. Software doesn't have an up. I could do this on its side. There's no natural up. This is not like building Lego. This is not like building anything out of bricks. Don't fool yourself. Let's try something different. So this is a very bottom-up approach. Let's try something else. So what we're going to do to prove our architecture, so to speak, I don't mean mathematical proof, I mean to try it out. It's an idea. Well, how do I know that that idea is any good? Well, let's start filling in. It's more like sketching. I've sketched the shape. Now I'm going to do some shading. Let's take a feature and run it through, and we will only put in the bits that we need. Yeah, but what about those? Maybe we could save time and do D, E, and F. Now, remember that whole thing about saving time? People often do things to save time. You're not saving time. What you're doing is you're stealing time from the present. That time can still exist in the future. There's no, you're not saving time. This allows you, by the way, to get things wrong at a limited scale. I can get something wrong, and then when I do the next thing, I realize, you know what? A little bit of rework. We spread it evenly rather than having it clump. And even then, we can just stop now, and we've still got something that works. But we've also demonstrated the architecture. Also, we are not wedded to the architecture. At this point, we may realize, there's a lot going on in E, more than we anticipated. We should break this up. Actually, the basic technology that E wraps is now different. And this is no longer quite right, so we're going to rework that. There's a lot of possibilities here. You can reshape and so on. It's still work in progress. You're not attached to it. So this is a very different approach that slices differently. So a way that's implied what I've just said, architecture is a hypothesis that needs to be proven by implementation and measurement, a quote from Tom Gilb. It's a lovely way of thinking about it, because what you're doing is you're basically saying, I have these beliefs. That's lovely that you have those beliefs. That's great. Are they good? I don't know. Let's find out. Let's build it. But when we talk about measurement, what do we mean by measurement? A very obvious thing here, when we talk about implementation and measurement, is I might be talking about performance. That's the most obvious thing. If somebody says, let's do it like this, let's add a cache here, or let's use this framework because that will be faster. You go, okay, let's try building it. Run some performance measurements, and you know what? That is faster. Excellent. Or actually, that's a lot of complexity, and it made almost no difference that we could detect. So we'll choose that's not the way we're going to go. We're not going to add complexity for no benefit. If, however, it gave us this massive performance improvement and made the code more complex, okay, maybe we take that. That's a trade-off. Literally, it's a trade. That's the way you need to think about all these decisions. And that's the interesting thing, is that we forget the English word trade-off. It's about trade. You're giving something in order to receive something. And you can work, is it a good trade? Oh, yeah. Here is the thing that I want. Better performance. I am prepared to pay a little bit of development complexity in order to achieve that. The thing that is most frustrating is, and what do we get? Oh, no performance difference that I can detect, but wow, the code's way more complex now. Well, that's a bad trade. I'm giving something and getting nothing back. But this is the point. This also works at another scale. This is not just about performance. This can be, there's all of these other things that people say. Let's do it like this because it'll be easier for developers to work with. If we provide interfaces like this, it'll be easier to extend. That's a hypothesis. How do you prove it? Well, you implement it. How do you measure it? Well, this measurement takes a bit longer. This is not, oh yeah, it's Friday tomorrow, so I'll do a performance, I'll come up with a prototype and do a performance measurement. No, we tried this, and in 1 month's time, 3 months' time, and 6 months' time, we review it. Did it make our lives easier? Yeah, actually it did. In fact, if we look at the defects and if you do the qualitative round the team, yeah, this was a lot easier, actually. Adding those in, that made it a lot easier. But notice the time frame of your measurement is not, we measured it this week. It's we measured it over a period of weeks. How many people ever make I see so many cases where people say, oh yeah, we did this because it would make this easier. Has it? Well, we never really evaluated that. Or, no, it hasn't. So why didn't you change it? Oh, yeah, I never really thought about that. Because they don't make it a first-class decision. So let's go back to something else I did and talked about earlier, which is the idea of pushing decisions into the future. There's kind of like a timeline that you want. Decisions we have deferred. We don't know enough at this point to make a good decision, but we need to know by this point. So let's find out what we can by this point. But there's also, we should probably review this idea. We added this because it would be easier for developers. We threw a question into time. We just need somebody to catch it on the other side. It's like, when should we ask? 2 sprints time. Okay, brilliant. Let's put a placeholder there. At that point, we can come back and say, has it made? Well, tell you what, when we look at the code, the developers are all working around it and avoiding it. Why? Because it's so complex. So it hasn't made their lives easier. Right. Well, now we have an answer to our question. This decision does not make people's lives easier, but it's a much longer term thing. We're very bad at noticing these things, but they pollute our systems. Now, that idea of understanding the shape of things also relates to team structure. So you can't really talk about architecture unless you talk about Conway's law. This is one of the most interesting observations. Melvin Conway, who actually spoke at this conference a few years ago, and is still very much alive and active on Twitter. Well, he has been active. I haven't really checked the last couple of weeks. Twitter's been doing other things. He made this observation. It was published in 1968 in Datamation. Basic thesis is that organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. He's not saying that that your code will follow a structure that is the same as your organizational structure. A lot of organizations have these lovely organograms, these diagrams of the company structure. It's about the communication structures. And communication structures are way more complex. Some of it is to do with organizational hierarchy. Some of it is to do with geography. Okay? Some of it is to do with, how things are laid out in a building. I worked for a team many years ago, and one of the most interesting things was I then changed team, but I stayed where I was sitting. But that team was upstairs. I tell you what, I got really fit. But I was a team lead. And eventually I had to give up my really nice office space to go and hang out with everybody else. Eventually I realized, you know what, it's just not making any sense me being down here. Because I knew that I could feel that was shaping my communication. But it's also about other things. It's to do with relationships that people have. The hidden communications in an organization. This person plays tennis with this person, so they know each other really well. Oh, that person's part of the smokers, so they all know each other. There's a communication network through the smokers. This guy has been here, in fact, I had this at one organization. This guy has been here forever. He's not part of the higher management, but if you want something done, you talk to Paul. Because he is connected to everybody, like mycelium in some weird way, So the point there is the actual communication structures as opposed to the imagined communication structures. It will shape, it exerts a force on the shape of your system. In one way, this is utterly unsurprising. The way that people communicate changes the way that they collaborate and the degree to which they trust each other. And I've seen this play out. Worked with a project that was 7 cooperating, I'm putting that in quotes, 7 cooperating companies trying to create one product. Oh my goodness, never again. I remember describing a particular situation, and I had one guy come up to me afterwards and said, Kevlin, were you on that? I was in there. I was one of the 150 people in this room. Yeah, it was absolute chaos. But the point is, we didn't trust anybody. We put in an architectural isolation layer to protect our subsystems and our code from everybody else's. It was kind of like, yeah, sure, we're cooperating. Okay, keep back. We had, our interfaces were bulletproof. We had moats. We had all the defenses available. Other people's code. Don't trust it. That was good reason not to trust it. And guess what? We all played that game. You can imagine that was not a good system. Progress was slow. Progress was political. You spend a whole day in a meeting arguing to change one method in an interface. That was my progress that day. I hated working on site there. So, yeah, there's a point here. It's not all that bad, but there is a simple point. Even when it's good, there is a shaping force. So that was kind of the whole motivation here. Now, what's interesting is that Conway actually described, therefore, an important idea. We have found a criterion for the structuring of design organizations. A design effort should be organized according to the need for communication. I would urge you to read this paper. It's only 4 pages long. You can find it online. It's even on Mel's website. It's actually quite rich in its observations. It's a beautiful piece of history, but it's very rich in its observations. But also, it will avoid you making the mistake. There's this thing. So, one of the most interesting things in terms of team structuring that I've seen in recent years is team topologies. Some really good stuff there. It moves beyond the kind of false dichotomy of we must have feature teams or component-based teams. It moves to a much richer view. However, they make one mistake. They have this idea, they call it the inverse Conway maneuver. I'm just guessing they didn't read the original Conway paper. It's not their fault. It actually originates in a ThoughtWorks tech radar thing a few years ago. The inverse Conway maneuver is exactly what Conway put at the end of it. There's no inverse to it. He is actually telling you the point of his paper is structure your teams because of how you want your architecture to be. That's what he's saying. Some people call this the inverse Conway maneuver. No, it's the Conway maneuver. It's what he actually wrote. It's only 4 pages long. I do recommend reading it. But the point there is you can take control of this. Again, it goes back to an earlier idea we had in the first half. Does this architecture, is this suitable for this team? Yeah, we looked at it from the point of view of skills, but now we can look at it from the point of view of shape. Yeah, so a friend of mine who used to work for IBM, he sort of visited 2 sites, and they were jointly developing something. And he kind of looked at one particular thing, and he sort of said, why have you guys got this package? Because those guys over there are the ones that need all the changes and actually need it, but you guys don't use it. Well, logically, the architect said it lives over here. Yeah, logically. But those are the, let me repeat myself, the people that actually need it and actually use it are over there. So logically, it should live over with them. Yes, but that makes the architecture ugly. Well, beauty is relative, but beauty is practical. It turns out that things that are practical are actually considered to be more beautiful from an aesthetic point of view. And the point there is just like, yeah, your beauty doesn't matter. And it's one of those things, Richard Feynman, the physicist, a beautiful theory can be slayed by an ugly fact, but that doesn't make it the theory any good. It doesn't mean you want to keep the theory. It means you need to bend to the fact. And ultimately, that will be the more beautiful thing. Hey, it works. Is that not more beautiful? Yeah, I overheard an architect actually complain once about what the developers did to his architecture. He said almost with disdain, they made it work. As if that was a bad thing. You know? They changed it so that it worked. It's just like, it was beautiful on the VM of his mind, on the whiteboards and all the rest of it. But the minute it hit reality, it just wasn't going to work. And you need to assume that. Your ideas are great. There's nothing wrong with the ideas as ideas, but they're all hypotheses. You need to try them out and find out. And you know what? Maybe that's not right. It doesn't mean it's always bad. It just might not be right for this system. That's the other thing we always have to use. Is there's a reason people say it depends. It's a reason why you can actually have a really good idea for one system, or you thought it was a good idea, and it doesn't work out. But then on another system a year later, you use it, and it's exactly the right thing. That's because it really does depend. The context is different. There are differences in the needs and requirements. So you need to recognize that some of those decisions are going to change. Now, one of the books I always recommend in this space that is wonderfully code-centric, but totally architecture-aware and very empirical. This is the most important thing. Adam Thornhill's stuff, really empirical. Your code is a crime scene. Wonderful metaphor. Importantly, he talks about the idea that you have this vast repository of data that you don't use. You have a source code history. In other words, this is the history of the system. This is what actually changes. Not what we thought was important, but what actually does change. You can find the change hotspots. That you don't need to say, hey, you know, I wonder what the tricky pieces of the code are. You can find out by careful query. There is a database of time and your code. We normally look at, I think we do a very bad job in terms of naming. We know that naming is hard. We do a really bad job in terms of naming because we call these things version control systems. Yes, it does version control. But even worse, the modern terminology is to call them repositories or repo because it sounds cool. Repository, that is the worst term possible. A repository is just a place you put stuff. It's not even important now. A repository is like, oh yeah, that's where we dump the code. Wow, version control is way better than that. But actually what it is actually a time machine. Or if you want Victorian kind of steampunk overtones, it's a difference engine. That's literally what it is. But it shows you the history of your system. You can track changes because what happened in the past is likely to happen in the future. You can find out what the hotspots are. You can find out what the stable bits of the code are. You can find out where the bugs live. You can find out so much. You can also find out, this is one of the things that Adam found, even though Conway formulated his law around the initial design of a system, the law has important implications for legacy code as well. He did read the paper. But you can actually see the shape of different developers and how they commit and interact. You can find, in other words, you have a simple way of testing many of your theories. I have an idea. That's great. Does it work? I don't know. Let's come back in a few weeks. Let's see how things flow. And then you can go and say, oh, yeah, that's proven. And we can take this a lot further to understand legacy. One of the most important pieces of writing on this in the last decade that I think is massively overlooked is a piece by Rob Smallshire. Predictive models, development teams, and the systems they build. He kind of looks at, he recreates models, and he looks at, okay, proportion of the code written by the current team. Let's imagine this team through time, okay? And so we kind of got like, just under the 3-year mark and so on. And there's this rather interesting observation of how much code is written. If you are now on this 20 years, if that code base is 20 years old, how much of the code was written by the current team? And to understand what we mean by current team, you need to understand half-lives. This is an interesting one, because the half-life is, we often assume that distributions fall into Gaussian shapes. They don't a lot of the time. And this is really nice. Half-lives of various entities in and around the software industry. Developers, 3 years. Windows XP, this was written 2014, so that's changed a bit. Applications, typically 6 years. CEOs, they last quite a long time. Lines of code, but they don't last as long as lines of code. FTSE 100 companies, classes, modules, my goodness, that is a long, this is the gross partition structure of your system. Remember that this is half-lives. That basically means that this is not averages, this is half-lives. This means, because 60 years back, it kind of takes you to the beginning of the 1960s. You might say, well, surely that's not the case. No, it basically means for a system that's been around for 10 years, whatever the partition structure of that system is, 10 years ago, about 90 to 95% of it is the same structurally. The coarse separations in your system. Of course, most systems are actually a lot shorter, but we're basically saying if we were to project this on this decay graph, things last a long time. But this is the really interesting thing. Rob then simulated this. He said, okay, what we're going to do is we're going to take a team of 7, we're going to play them out over 5 years, and we're also going to have staff turnover. So these are the contributions of the developers to the code base. And where you see a black line and a shift in color, that developer has left. But notice the effect of their code has a long-term shaping force. In other words, this is a time-based version of Conway's law. Long after you are gone, people will be cursing you. Or thanking you. Let's be optimistic. So this is the observation Rob brings to us. The state of a system reflects not only the organization, but the organizational history and the flow of people through those organizations over the long term. What I mean is that the structure of the software reflects the organizational structure integrated over time. That's such a cool way of looking at it. And that's a really important thing. Again, whatever our logic for decisions is, it's ultimately, people, you may hear this term every now and then, people say, oh, it's software development or software architecture. It's socio-technical, which itself is a great word to just drop into a conversation. But it is socio-technical. There's the technical side, which we regard as logical and rational. But then it's all about people. And it turns out we are not as logical and rational as we like to think we are. And it's about how we communicate. It's about preferences and what was easy on that Tuesday when we did that, and so on. That all of the little things, as the system grows, are left. So the tiny system that begins, you make a decision, and it was just a minor thing. You put something in a separate file, or you didn't. 10 years down the line, that's grown into something that is very significant. I had this with one particular team, absolutely fascinating team. It was a system developed in 2 cities, one in Asia, one in North America, and they jointly developed this. And there was a fault line, like the San Andreas fault, running down the middle of the system. And on one side was Asia, on the other side was North America. And it was really obvious. And I don't just mean the coding style, I mean fundamental decisions. The nature of time being one of them, the threading. The other was the fact that on both sides, they ended up with a large in-memory data structure that was almost but not quite identical. Duplication, and then they spent a lot of time trying to synchronize these, which in a multi-threaded system means there's a lot of locking. The funny thing is, I guess, so that you had loads of this stuff. And you change data structures and models as you cross the border. You are now leaving the North American sector and moving to the Asian sector. Please change your currencies and your data abstractions. And there was a lot of toing and froing here. What was funny is after working with them for a few weeks, they said, what recommendations do you have for performance? I said, you need to kind of eliminate the duplication in your code and have a more uniform style. Yeah. But how do we make it faster? And I said, I just told you. Because I think the biggest thing is the fact you've got 2 different data structures that actually really are the same job, and you're trying to synchronize everything. And so they got a 200% performance improvement by unifying the data structures. That was, given that they'd just spent the last 3 years trying to get a 25% improvement. This was kind of, I did tell them, by the way, don't release it to the customer all at once, because otherwise they'll get used to this. Yeah. But what was interesting psychologically was one of the conversations I had. I remember chatting with the guys and they said, oh, that's the American code. And I said, when did you guys get to do, it was originally developed in both places, but then it was moved all to Asia. I said, well, how long have you guys been, how long has it been under your stewardship? And they said, oh yeah, well basically we got custody of the code 4 years ago. And I said, so that's not the American code, that's your code. Oh. No, it's the American. It's been yours for 4 years. I have bad news for you. So there's a bunch of other stuff. When we think about architecture, we've got the qualities here. Qualities of development over time. But we have this terrible term that we throw around. Non-functional requirements. Oh dear God, please don't use that term. I know it's really hard not to, but let me just say as a native English speaker, this term means nothing. Non-functional. What does non-functional mean? Non-functional means broken. What are your non-functional requirements? We'd like it to crash every Tuesday. Okay, we can arrange that for you. Yeah? Non-functional, that's not a good thing. My washing machine is non-functional. Oh, shit, we should get somebody to fix it. What are your non-functional requirements? You'd use that language. No. Sometimes people use other terms for this, cross-functional, quality requirements, and so on. It's a much bigger landscape. I do like a good ISO number. Here we go, 25010. Oh man, this has got such a succinct, easy title. You'll want to use ISO 25010. Here's the title. That's just the title. Good God. System and software engineering, systems and software quality requirements and evaluation square, system and software quality model. Oh, dear God. Okay, let's just stick to 25010. But it's a really good breakdown of all the quality considerations that we might have. There are 8 topics here, 8 categories. These ones are functional. And these ones are non-functional. See how useless that term non-functional is? It also shows a remarkable lack of imagination. You know, later I am planning to have a not beer. For breakfast I often have not tea. You know, often I have not cereal, but sometimes I have cereal. The point is, it's not a very good classification scheme. What is that? Well, I'll tell you what it isn't. No, I asked you what it is. Tell me what it is. So there's a rich landscape here. This is actually a really good breakdown. It's a good checklist. For those of you who my talk earlier today, I gave a very simple one that we can say is code focused. This is very much the system as a whole, but a very simple one that is code focused. Just looking at kind of right-hand rule. I broke it down into functional qualities, operational, so a lot of those performance capabilities, developmental. These are all kind of included in that. For some reason, that alignment's gone slightly off, but no worry. So we have all of these considerations. We also have, when we talk about various performance aspects, we also need to understand that lovely observation from Kirk Pepperdine in 97 Things. There is a relationship between how we approach things. Sometimes people will sacrifice certain qualities to achieve others, but sometimes they sacrifice them too quickly. More often than not, performance tuning in a system requires you to alter code. When we need to alter code, every chunk that is overly complex or highly coupled is a dirty code bomb lying in wait to derail the effort. Sometimes people say, oh, don't worry, it's messy because it's faster. Or rather, I'm trying to make it faster. And then you leave a trail of destruction. And next time you come through, oh, I don't know how to optimize this. It's so complex. You create and this is the interesting thing. Without meaning to, you create work in future. This ties back to our perception of architecture. What is architecture? It's where developers spend their time. So if you start leaving things all through the code, you suddenly realize that from the bottom up, don't worry about the top-down view of architecture, from the bottom up, you are leaving something. So code quality has a direct impact. Code quality is a quality of your architecture. It's not just a detail. It's a form of friction. It's a form of resistance that will reduce the effectiveness of your effort. So, as he says, the first casualty of dirty code will be your schedule. I made a point this morning about talking about habitability. So this is where I got the term from, this book by Dick Gabriel, Patterns of Software. It's actually a series of essays. And he talks about the characteristic of source code that enables programmers, people coming to the code later in its life, to understand its construction and intentions and to change it comfortably and confidently. That's what we want. Yeah? Habitability makes a place livable like home. That's what we want in software. Developers feel at home and can place their hands easily, on any item without having to think deeply about where it is. That's the whole point. You're creating an environment for yourselves, your future selves and your colleagues to work in. And if you start leaving junk around, then people will trip over it. Yeah. So, and then if that becomes the way that you build the architecture, that becomes the architecture, particularly when new people join and say, oh, that's how you're building it. Okay. And it leads us to things like the broken windows theory and all the rest of it. It's just like, well, nobody cares about this. In fact, the best one you can have is the conversation of like, you do the simple analysis. You go through, that's really interesting. All the code quality problems seem to be in this part of the system here. Part D. And you go to the people who A, B, and C, and you go, Alice, tell me about D. Oh, that's Doug's subsystem. Oh, that's where all the complexity and the bugs are. Yeah, that's Doug's subsystem. You're going to have a chat with Bob. Tell me about that's Doug's. Yeah, we had a lot of problems with that code. You know, have a chat with Charlie. Yeah, that's Doug. So can I have a chat with Doug? No, Doug left 2 years ago. It's exactly like that's been your code. So then you go back. You rewind time. When Doug left, that code was great. But now everybody's just like, well, it's not my code. Yeah, I'll just do just a quick fix. 2 years of quick fixes is now your architecture, your architectural bottleneck. Yeah, that's the thing. People, so sometimes, oh no, it's architecture is the gross structure. No, it's the little structure as well. If you do lots of little things, it makes one big thing. You know, it's a really simple idea. We try and teach kids this. I think we need to teach developers this as well. You know, but this also then ties into this topic of technical debt, which is a very compelling and communicative metaphor, because we all have some understanding of debt. To choose an effective metaphor is quite difficult. People have tried different metaphors over time for various things, and it's not always obvious that they work. Okay, I think my favourite one, first company I worked at after university, was the idea of entropy, software entropy. I found that really compelling, but I had a physics degree, as did half the other developers. So entropy to us made a lot of sense. And then we tried explaining it to people that might not have had a physics degree. Who knew? It turns out that it's not a great metaphor if you have to explain the basis of the metaphor to explain the thing that you can't Yeah. A metaphor is a way of understanding something that is difficult to understand in terms of something that is already understood. If I have to explain the thing to explain that, then no, it doesn't work. Code rot. That's not bad, except for the problem that code doesn't rot. If you leave it, it does exactly nothing. There is some yogurt I left in the fridge at home before I left for Lithuania. I'm really hoping that my wife notices that the date is over and that I don't return tomorrow to discover that actually, yeah, it might be a little bit past. And if I left it 2 weeks, well, that's new life. The point there is that nature has processes, code does not. We are the motivator. We are the biological entity that causes code to change. It turns out if you remove us, the code doesn't change. So rot and decay, these are not the right. Erosion, again, that's a natural process. So it's not quite the right language. So technical debt's very powerful. And Martin points out, Martin helped popularize it. Technical debt, the idea of the debt metaphor came 30 years ago. In this metaphor, doing things the quick and dirty way sets us up with a technical debt, which is similar to financial debt. Financial debt, it's a really powerful metaphor. But there is a problem. And the problem comes with this phrasing. In the original description of this article, which unfortunately Martin has since revised, and it's a shame, I think you can go back on the web archive and look at it, because this article helped popularize technical debt. I was certainly using the term debt, quality debt, design debt, and technical debt in the late 90s. But unintentionally, Martin also gave a value judgment here. Quick and dirty. In English, that's not a positive thing. Okay? We are saying it's a bit of a hack, and that is not quite what Ward was trying to communicate. So we've come to associate technical debt. As I said this morning, technical debt, a lot of people say, oh, technical debt is a bad thing. We have technical debt in our code. And it's like, that's not necessarily a bad thing. Let's look at what Ward actually said back in 1992. Shipping first-time code is like going into debt. A little debt speeds development, so long as it is paid back promptly with a rewrite. In other words, he actually said he wasn't trying to model the problems of code. He was trying to model how we borrow from time. Debt is a borrowing. That's the metaphor. It's a borrowing, and there's a repayment. You are borrowing from yourself. From your future self. That's what you're doing. You're taking a borrowing. You're taking a loan. You've got to pay it back. Otherwise, well, the danger occurs when the debt is not repaid. Every minute spent on not quite right code counts as interest on that debt. Ward was not offering us a model for describing bad code. He was offering us a model about trades and loans. And then, of course, there are loans that go bad. But somehow we've ended up just assuming that that is exactly what technical debt is, and that's not. Martin also described a number of other distinctions. He said useful distinction isn't between debt or non-debt, but between prudent and reckless, wise or unwise debt. Not just is there a difference between prudent and reckless debt, there's also a difference between deliberate and inadvertent. Deliberate, we know what we're doing. Inadvertent, we don't know everything. We do things accidentally. And so, in fact, you can end up with kind of this model of debt here, let's draw this one out, we can end up with this idea of a quadrant diagram, and we can have the kind of the prudent. Actually, no. Let's just do this like this one. Let's do this one as deliberate. We know what we're doing. Inadvertent. Accidental. We didn't know enough. Prudent. Wise. We know what we're doing, and we understand the consequences, and we have a repayment model. Oh yeah, we're doing this. We're taking this shortcut here, but in the next after the next release, we're going to repay that one. Or actually, at this point, we don't know the best way to do it, so we're just going to put in this workaround, and that should be fine for the moment. But we will pay that back. Do you remember that little kind of idea I started talking about a timeline? Yeah, you don't take out a try this with your bank. I would like to borrow 20,000 euros, please. Oh, okay. So what loan conditions would you like? Would you like a 12-month payment, a 24-month, 36 months? Would you like 5 years, 10 years? I don't want a time constraint on that. Just let me know if you're successful with that, because then I think we can all go to that bank. The point there is that's the whole point. You're taking out a loan. Put this on your timeline. Where are we expecting to pay this back? You know, give me a range, because that's the important thing. Prudent. Reckless. And it turns out that the prudent side is absolutely fine. Because, I mentioned, my wife and I took out a mortgage, we got a house, okay? What was the benefit? We got a house. Oh, cool. Was it arbitrary? Was it random? No, we had structured payments. It was structured over time and had contingency if we needed to opt out and various bits and pieces. Oh, okay. So it's not arbitrary, it's not random. Okay, it's well managed. It's managed. That's the key word. So I tend not to use quite this language. I tend to talk about managed versus unmanaged. So I tend to think in these terms that what we're looking at here is we manage. We have managed debt. Okay, this debt is managed. On this side, it's unmanaged. Oh, yeah, we know it's a workaround. We'll pay it back. We'll fix it at some point in future. Do you know when? Have you ever done this? I had this with one team. Well, we've never actually fixed anything we said we were going to. Or no, I'm not accurately portraying the conversation. The conversation went like this. Oh, let's just work around that and we'll come back and fix it later. I laughed. That was how the conversation went. So what? We intend to. And I said, have you ever done it? No. Well, that's why I'm laughing. Because there's no evidence that you're good at repaying your debts. Yeah, that's an important thing. The other consideration is that sometimes we don't know the best way. We operate with incomplete knowledge. Sometimes we discover, you know what? When we used that framework, we did some really crazy stuff. And we didn't need to. It turns out the framework already did that stuff for us. We just didn't know. Well, that's fine. You're not, the trick is you don't have to know everything, but what do you do? What's the prudent response? And now we know. And so now we tell other people, and now we make sure that those problems no longer exist in the code. We repay the debt now. As opposed to one team, I spent a lot of time having a very deep conversation about, oh yeah, this thing. In the example this morning, I used a very simple table lookup. They had ended up with a monster function. This was actually ATM code. A monster function that was guarded by two people. You cannot change the code in this because nobody understands it. This was a switch statement within a switch statement within a switch statement. It had kind of complexity that would rival any AI system. And it was probably more malicious than Skynet. And it was just, it's just the fact that you actually... So when people say, we need to add a new event, you'll have to go through the proper channels and speak to the right people for that. Because it's such a delicate thing. You can't just go in there and just add an event. Oh, good grief. No, that would be way too easy. So I showed them a number of techniques for refactoring and rationalizing this into a simple table lookup where somebody can say, out of a team of 20 developers, you go, yeah, we'll just add an event. There we go, done. No guardians, no keepers at the gate preventing you from doing this. And we had a long discussion, and they said, this is really good. Oh, this is great. Thank you, Kevlin. Yeah. I said, so should we talk about how you're going to roll this one? Oh, we're never going to apply this, but thank you. It's just, I just, you know, it's just like, yeah, it was just like, but we've solved a fundamental problem here, a bottleneck in your development that you didn't realize. Switch statements have a habit of getting bigger without you realizing it. That's in this quadrant. They didn't know. That's fine. You're not supposed to know everything. But now they have the knowledge, they're not going to use it. They feel that that opportunity is dead. So they were now going to be dominated by, you know, the bottlenecks and issues that they already had, even though we had now solved the problem. So we can look at this from another point of view. We can see that this axis is the cause axis. What is the cause of our debt? Intention or ignorance? This is the response. And how do we respond to that debt? Do we do so prudently or recklessly? So there's a lot of ways we can think about this one. So I wrote something for the O'Reilly radar. It was quite an interesting one. Technical debt. So technical debt is not the cost of repaying the debt; it's the cost of owning the debt. And this is really important because sometimes people will try and talk about the cost. They will say, "Oh yeah, we have technical debt on our dashboard." No, you don't. What you've got is a made-up number that has no meaning and nothing to do with debt. Especially if it's a currency value. Oh yeah, our technical debt is worth this many euros. Well, the one thing I can tell you is no, it isn't, because it's a metaphor. It's not actually financial debt. That's the whole point of a metaphor. You don't know enough to be able to justify that number. It's just bad science. But sometimes people will say, no, we've estimated our technical debt in hours. Now that's certainly an improvement. In other words, how much time to repay this? How much time to fix it? But that's not your technical debt. Your technical debt is not how much to repay the debt. The debt metaphor is the cost of owning it. That's not the same. What do I mean by that? The message of the debt metaphor is not a measure of the specific work needed to repay the debt. It's the additional time, effort, etc. added to the past, the present, and the future. It's all of that effort, not just today, this is what it costs. It's all the extra work you had to do in the past because of the debt, and all the extra work you'll have in the future if you leave the debt. That's what it is. That's the whole point of the metaphor. It doesn't matter how much the mortgage was for when my wife and I bought the house. It turns out that's not what we paid. We paid more. By owning the debt, it becomes bigger over time. But there's also another lovely metaphor. I kind of think my theory of tech debt is that housework is the correct metaphor for the thing we call tech debt, von Lamb. But we can't use it because tech has been made up of people who don't do housework or manage housework being done. It's not a bad metaphor. And this morning, I also talked about the fact that most of the time we're focusing on this. The real issue we're trying to address is technical neglect, which is slightly different. Now, let us look at... I'm going to skip a couple of things. I was going to say something about ADRs. No, I will, because I did say earlier on I would say something about them. So I'll borrow Stefan Tilkoff's quote. Architecture is a property of a system, not a description of its intended design. That description of its intended design can be valuable, but that's your original intention. That's interesting, but what happened? That's the beginning of the story. That's not the end of the story. We need to see how it played out. Our knowledge changes, but our requirements change. Now, there's this rather interesting book that was published in the 70s, Timeless Way of Building by Christopher Alexander, that kind of helped, that and his other books, help kind of create the patterns movement. Patterns are kind of widely misunderstood. I'm not here to teach you about that, but I want to look at a really important thing from an architectural perspective that I have found incredibly valuable that I learned from reading this book. A really simple idea. Every pattern is an instruction of the general form. The context, the forces, the conflicting forces, the configuration. Let me translate that to you. Context. We're trying to solve a design problem. This is not just to do with patterns. This is actually, you replace the word pattern with design. But Christopher Alexander was taking a very general view of design. Context. Where does this situation occur? What is the problem we're trying to deal with? You know, is it a we are working with threads in Java kind of problem, or we are working with some kind of entity model in JavaScript kind of problem? In other words, give me the situation. Some of it's technical, some of it's to do with change, some of it is to do with technology. What are the conflicting forces? Let me translate that. What's the problem? What is the actual problem? So what's the situation? What's the problem? And configuration, don't confuse that with application configuration. What he means here is structure. You will notice that everything he chooses begins with the letter C. That's why he chose it. These days, we would say context, problem, solution. In this situation, we have this problem, and here is a proposed solution. You know what? This is not just patterns. This was the most important thing I learned from this book, was to think of design as a kind of a conversation. And sometimes it's not intentional. Sometimes you don't know you're solving a problem. But when you look back, you go, oh, yeah, that's the situation we were responding to. And we responded based on what we knew at the time. So we can break it down. And that's the problem we were solving. And instinctively, we did it. But what you can do is break it down to this three-part narrative. Really simple idea here. And you can actually do this empirically. Is this design good? Well, how do we know that a design is good? The problem is real. It turns out these two questions are absolutely brilliant. They are so simple, and they are embarrassingly simple, because sometimes it causes you to think, actually, I'm not solving a real problem here. I'm solving an imagined problem. And the problem is, if you have a good imagination, if you have a very poor imagination, you will be done very quickly. But if somebody says, I want you to imagine all the kind of scenarios and all the, oh, yeah, we're going to design for the future and I've got a good imagination, you will be there for a very long time and your results will be very complex. But is the problem real that you're dealing with? If it's not, that doesn't mean just ignore it. It just means make a note. That's interesting. We should keep our eyes open for that. But it doesn't mean ignore it and forget it. It just means don't integrate it into the code right now. The configuration solves the problem. Let's translate that for you. The solution is a solution. You'd be surprised by how many solutions are not solutions. They just feel like solutions. Oh, I do this because it feels good. I adopt this idiom because but it's all boilerplate code. Yeah, but I feel good writing it. Is it actually solving the problem, or are you creating more problems? In fact, he offers us a more precise view. Means that we can express the problem, blah, blah, blah. It's an empirical question. Configuration solves the problem. Means that when the stated arrangement of parts, when the solution is applied, the conflict can be resolved without any side effects. By side effect, I'm not talking functional programming here, I'm talking side effect like medicine. Yes, this will solve your headache, but your arm might fall off. The arm falling off is a side effect. Okay? So there's the idea of when you apply this, does it cause more problems? It's a really simple idea. Ask those two questions in any review or for any practice. You'd be surprised how powerful they are. I have stopped architects dead in their tracks. Yeah, but what problems does this solve? Well, it solves the problem that we didn't have this pattern implemented. It solves the problem that we weren't using this framework. What is the problem you solved by adding XML here? The problem we had was that we weren't using XML. And now we are, but that's not a problem. Yes, but my CV does not have XML on it, so therefore... So you get to the heart of the matter. Now, what's this got to do with ADRs, architecture decision records? It's got everything to do with it. ADRs, Michael Nygaard came up with these just over 10 years ago. And an ADR follows exactly the structure. He actually says, it follows Alexander's pattern form. Basically, you document. You don't put it in comments. You don't put it in Word documents. You don't put it in HTML. You put it in a markdown file in the same place as your code lives. This is a really important, it's such a simple idea. Because one of the biggest problems we've ever had with documentation is that the source code is over here, the documentation system is over there. Well, people respond to cyber things the same way they respond to physical things. It's like if it's in a different place, I have to do a different login and I don't do the same thing. Put it in the same place as the code. Don't get clever with the notation. Just use Markdown. If you want to put a UML diagram in, that's fine. Use plant UML notation or something like that. That's text and it's versioned. You version it alongside everything else. You focus on, here is what we've just done. This is the situation. Here is the proposed solution. The situation and the issues. Here is the proposed solution. And then you have the status. That allows you, by the way, to have design ideas that you never implement. But you don't want to lose those ideas. You want to make a note of them. Oh, that's a really great idea. Maybe not for this system. So in other words, proposed. But we never applied it. So it's got a version tag. Consequences. What are the pros and cons? What are the situations? If we do like this, then it can actually use more memory, which is a negative, but it in our current system, that's not going to be noticeable. But it gives you a heads up as to when it might become a problem. You can add other tags as well, according to the part of the architecture. My favorite one is add a date that you should review this at. And you can now have an automated thing. Let's come back to this decision. Let's implement this. It's accepted. In fact, we can have a much broader thing, proposed, accepted, implemented. We can come back to something and say, you know what, that decision is no longer relevant. Let's deprecate it. Okay. And now we've taken it out. So now it still remains in the version control system, but you can now review the history of the system. And don't get clever with this. I did this with a bank earlier this year and say, oh yeah, we use ADRs in SharePoint, completely separate from the code. And then we did an ADR exercise and we had some issues. It turns out that all those years I spent writing patterns, it's just like, yeah, there's a really easy way to review these, and it's very, but they had the granularity of their things were wrong, and they were enormous. What they'd done is they'd just turned their bureaucracy. Yeah, here's our design. Well, we're very bureaucratic, so now we've got a new name for it. It's called ADR. So they just did that. It's the same way that a lot of organizations use SAFe. Okay, it's just like, this agile stuff. We ought to do something, but how can we be agile without actually being agile? SAFe, excellent. So there's a bunch of stuff here that's kind of quite valuable from this point of view. And I'm not going to talk about models deeply, but I do want to, if we have more time, I talk about models. But I'm just going to point to Eric Evans's work. The idea of models being a very important idea in domain-driven design. And models is not necessarily something that is intrinsically graphic, but there is something useful here. It is about the idea of the medium of the system. The stuff of our architecture should be kind of stuff that's real. By using the model-based language pervasively and not being satisfied until it flows, we approach a model that is complete and comprehensible, made up of simple elements that combine to express complex ideas. Every system has a model. The question is not, does a system have a model, but do we recognize that it has a model? Just like every system has an architecture. Do we recognize that it has an architecture? Yeah, that's, whether or not you recognize it, it's still there. But there is an implied model about how the business works, about how the software works. And that gives us not only information about the vocabulary, but it also allows us to partition the system according to, and break it up meaningfully, because otherwise we can end up with the problems that many people encountered in architectural efforts in the 90s and 2000s. This was really popular, of a unified entity model for a whole organization. There were different names for it, but I encountered this a lot. It's, oh yeah, we've got a central architecture team. In fact, there was one company, I remember, this is a side note, but I just said central architecture team. There's one company I visited and they said, oh yeah, Kevlin, their greatest achievement was their team name. And the guy told me this at the pub. He said, yep, we finally come up with a name. They were just disastrous. They were also a banking organization. That's one of the things interesting, is accidentally a side effect of visiting many companies, is you kind of go, I am not putting my money with them. I've worked with their developers. They're lovely people, but utterly clueless. But the core team were the cat and dog team, the component architecture team and distributed object group. That was their finest creation. Everything else was downhill. It was just frightening. So, the whole point is, you end up sometimes with we are the center of things, we own the architecture, and we're going to have a unified model for everything. That's really hard. That's really hard. Even if you think you're dealing with a unified domain, it's hard. In medicine, you have the idea of oh yeah, okay, we have patients. You very quickly discovered in the medical domain there are lots of different kinds of patients, and different parts of the organization have different views. If you try and create a unified patient model, you will spend all of your time having political discussions. And what will the developers do? They'll just get on and develop something that works. And it probably won't fit with the other things that work, but at least something works. And that's a real issue. So you have these ideas of partitioning, bounded context. You say, right, inpatients. We have outpatients. We have you have different parts of the organization, and you say, right, this actually makes a meaningful architectural division as well. Whoa, you right there? No, I think that was a gravity thing, not an oxygen thing. So there is an idea here that we want to make sure that we understand the nature of the thing we are trying to build. Domain experts should object to terms or structures that are awkward or inadequate to convey domain understanding. Developers should watch for ambiguity or inconsistency that will trip up a design. Now, there's a number of interesting things that happen here. One of these, in terms of communication, is you want to avoid the situation that I encountered with one group. I ran this workshop, and these are kind of like Java enterprise people, and I gave them a simple problem. We're just going to do stuff on flip charts and so on. And I gave them a simple problem. I said, okay, let's just come up with kind of like a basic domain model, and then we'll kind of like just sort of see plausible ideas, and I'll throw ideas at you, and you'll see how you respond, and just like, you know, raise questions. I want this to be, I don't want your diagrams, they're not a commitment, they're an exploration. It was a very important idea with modeling, is it's more to do with the ing than the models. The modeling is a process where we kind of communicate, and maybe the models are useful, maybe they're not, but the fact that we cause communication is the most important thing. I remember one particular group, yeah, everybody in the room was doing really well, and in one particular group I kind of went up to them. I said, so yeah, walk me through this. And they walked me through various layers of enterprisey Java stuff and all the rest of it. I said, okay, yeah. And I'm not really seeing any of the domain stuff that I put in. Oh, yeah, we were going to come up with the architecture first, and then we were going to come up and ask you what the requirements were. I might suggest to you this is not a great way of thinking about it. It was almost like we come up with the architecture, then we plug in the requirements as if they're like an optional extra. You know, it's just like, yeah, I like a little bit of pepper on my food, and possibly, you know, this is sprinkling of seasoning, sprinkling of requirements. So, no, that's not how it works. Those shape the system. They get you talking about the system. They're substantive. They're real. But also there's an exploration here. So a particular team that I visited, was doing technical coaching for a number of years ago. There were a lot of unknowns in what they were doing. This was all new territory. They were a new team. This was a new domain for them. The requirements were far from certain. And a couple of guys had written up a couple of user stories, and there'd been a couple of diagrams and stuff like that. I said, and the architect said to me, what would be interesting now is if we take 3 of the user stories, and we had 12 developers, and we split them up into 3 groups of 4. I said, that's a really good idea. He said, yeah, we do 3 user stories, 1 each. And I said, I have a better idea. We give them 1 user story. Each team, because I remember what our bottleneck is at this point. Lack of knowledge. We don't know. We don't even know these guys can work together. They've not worked together. The domain is, there is a lot of unknown. This is not a productivity exercise. At this point, our challenge is knowledge. We genuinely don't know enough about the domain. So let's get them all to model the same requirement and see what we get. No surprises. We got 3 different models. But what was fascinating, and this was new to me, I visited room 1, and 3 breakout rooms, visited room 1. I was like, oh, okay, yeah, okay, this makes sense. Went into the next room, it's just like, oh, there's a difference here that is interesting, and I had not noticed it. A fundamental difference. Let me simplify it for you in a very particular way. I want you to imagine that you've got a calendar system. This is kind of as close as I can get to it. A calendar system. And you book a meeting. And then you say, we're going to book a repeating meeting. Now, that's interesting. Is a repeating meeting a meeting? Or is it lots of meetings? It's a really interesting question of classification, and this is the closest I've been able to find to what these guys discovered. Room 1 thought about it one way, room 2 thought about it another. Walked into room 3, they're arguing. They've discovered there are both ways. Or more to the point, they're disagreeing. Because they want the one true answer. The point is we don't have enough knowledge collectively. We're pooling our ignorance, but what we've made is a discovery of uncertainty. Hey, guess what? There's 2 implied models here. We need to talk to somebody who knows about this stuff. Yeah. In other words, we use that to highlight that, and actually that has very important implications for scaling. So let's kind of bring this one, kind of land this bird, with an observation that when we talk about architectures, we need to understand relationships. So this nice piece by Gregor Hopper. What is the relationship between developers and architects? Do we need architects? And you will find some places will tell you that you need architects. You'll find other places that tell you you won't need architects. Both of these are wrong, in my view, because they are trying to answer a complex. It's a little bit like asking, what is the right way to produce music? What is the right instrument to produce music? I happen to play the guitar, not necessarily very well, but I don't go around saying piano is wrong. Piano, we don't deal with pianists. That is the wrong way to produce music. I happen to like music, playing, music that can be performed in a band. But that doesn't mean that a person singing on their own with a guitar is wrong. It doesn't mean that an orchestra is wrong. It turns out the same thing for architecture and architects. We have this kind of approach. We have the benevolent dictator. Yeah, there's an exclamation mark for a reason. Be very, very careful with this one. This can create opposition. It can create us and them. But it can work in the right sense, as long as it relies very much on the personality of the individual. Perhaps a non-dictatorial approach. Primus inter pares, first among equals. Architect is a member of the team. One of the biggest problems with the cat and dog team I mentioned was they had a real us and them thing going on. And when I worked with kind of hung out with the developers, there was a real them. And then you go in and talk to the cat and dogs. It's how the developers don't understand what they're doing. They're stupid. And the developers are kind of like, yeah, we tried implementing that. It doesn't fucking work. Bunch of idiots in that team. Cats and dogs. Woof. Meow. The point there is if you're not part of the team, you're not part of the team. And that, notionally, also, that person may not be called architect. That's the other thing. Sometimes we have an architect and we don't recognize them by name. They're just a team lead or something like that. They're a tech lead of some kind. I had this particular experience with a team where a few years after I was on it, one guy said, yeah, I thought, Kevlin, I learned a lot about architecture from you. As an architect, you were really good. And I was just like, I wasn't an architect. I was just there. I led the design effort, but when I look back, I thought that was a role I played. I just didn't know that I played it at the time. Nobody called me that at the time, but I did play that role. And you see that in a number of other teams. Sometimes it's important that that individual has a title for certain organizational hierarchies and areas of responsibility. That it depends on the political games you're playing. But that's fairly successful. Also successful, architecture done by team members. It's across us. Perhaps we are all ultimately making the decisions, but perhaps some of us are doing so more intentionally and with more mentorship than others. But not one of us. We actually exchange. You find this kind of structure very particularly on small teams works really well. It might not work so well when you have a distributed team. You may favor one of these ideas. You sometimes, and this is why the it depends answer, do we need architects? Well, what's the problem you have? We have no problems. Do you have an architect? No, in which case, there we go. You don't need an architect. Do you have a problem that is solved by adding a role that helps communication and listens and coaches? Yeah, let's call that person an architect. That might be the thing that helps. But the one you got to watch out for is this one. Oh, it just happens. Nothing just happens. You have shared irresponsibility. Oh, it just happens, it's emerging, it's organic. No, there are ways of doing evolutionary architecture that are intentional and guided. It's not accidental. So you need to kind of understand where you are on this spectrum. And with that, I am going to end the day, if I can just find the end quote. There we go. From Ralph Johnson. Second time today I realised I've referred to Ralph Johnson. Gang of Four guy. Hal Johnson for CDs. Architecture is the decisions you wish you could get right early in a project, but you are not necessarily more likely to get them right than any other. It's one of those, you go, oh, I wish we had done this. Oh, that was architectural. But if you had a time machine and you did it all again, you'd probably miss something else. Because we don't know the future. That's the whole point. Architecture is a sensing, it's a probing thing. You're trying to figure stuff out. You're throwing ideas out. Some of the ideas will be good, and some of them, time will toss back at you and go, that wasn't such a good idea. But you've got to pay attention to them. It's a constant activity of experimentation. It's not something that's static. Sometimes people take the wrong message from building architecture. They say, oh, building architecture is static. No, it isn't. It's fascinating if you look at buildings evolve over 100 years. They are not the buildings they were 100 years ago. They change. It's just that the change is over a long period of time. Our software changes before our very eyes. 50 years becomes 5 years. And we think, oh, that changes fast. Buildings change just a little bit slower. That's actually one of the most interesting things, is when you start understanding the metaphor's power over time. But that's the key thing. Time is the ingredient, and observation. So, it is now time to be done. I hope that has been helpful. I hope we have not deprived you of too much oxygen. I am going to be around, hanging around for coffee and whatevers and drinks, and, so if you have any questions and any thoughts, please come up to me afterwards. That link, I'm now going to update, but the best time to update it is probably in about half an hour, because I'll have just, maybe 10 minutes. It depends how long. I've just got to adjust a couple of slides. But I will upload that. Alternatively, you can DM me or whatever. Anyway, thank you very much.